Hello there. My name is Ryan Lewis, and I'm happy to welcome you to this course, AWS Developer Designing and Developing. If you've come to learn the ins and outs of AWS, then you're in the right place. This course has a few objectives, but the most important is that your understanding and proficiency with developing in AWS will have leveled up by the end. This course is intended as a follow-up to my previous course, AWS Developer Getting Started. I will expect familiarity with many of the most common AWS services, so if you haven't watched that course yet, then I definitely suggest taking the time to work through it. With that being said, this course does cover many services already covered in the previous course. The main difference is the approach and details that we'll be covering. The Getting Started course's goal was to really get you familiar with the multitude of AWS's offerings. This course takes that familiarity and aims to make you moderately proficient at developing in AWS by adding even more detail and information. Additionally, the focus for this course will be on the development side of AWS and not cover infrastructure-related services like VPC or IAM. For this course, we're going to focus on taking a web application and integrating it into AWS. In the process, we'll create and modify services using multiple different methods such as the CLI and SDK. I'll take special care to include specific details about each service we're interacting with that should help you understand how to design your AWS architecture for your own applications. Developing an application in the cloud is not always quite the same as typical non-cloud development. As companies migrate to the cloud, more and more developers are getting their first taste of operations and infrastructure as they're directed to do their own cloud deployments. In your past experience, you may have been used to just building your application and then handing it over to another team or engineer to do the actual deployment of that application. Because of that process, you may have thought of your application as only the code you wrote and other parts as outside of your domain. But as with everything in tech, the world is changing and operations concerns are consistently falling into developers' laps. I believe this is a good thing and will ultimately improve your career as a developer. It also does something else though, and that's a sort of mind expansion. Once you can utilize everything that AWS offers, it changes how your applications work and how they're designed, which really changes the way you think about your applications. I've experienced this personally over the past few years when I began steady AWS development, and it's only improved the quality of my work. I like to describe cloud development like this. Basically, when you begin thinking about a new application, you'll want to start with the infrastructure. There are certain decisions you'll need to make, such as computing, persistence, routing, and AWS gives you multiple options for each. Each decision you make fundamentally shapes how your application is structured, and this approach is what I like to call cloud development. With each service that we cover in this course, you'll add another tool to your application development tool belt. And when you approach a new feature or application, you'll be able to consider how certain AWS services might best be used. Eventually, your application will be a distributed and scalable combination of code and services. This adds resiliency, improves maintainability, and ultimately results in a better application. The services in AWS are grouped into domains. In the AWS console, you can see how they've grouped them by the application concern each deals with. Some examples are compute, storage, and database. Because there are quite a few services, it helps to group them conceptually and provide some context to each. In this clip, we're going to talk through each AWS domain to help you understand what each one contains. The first and sort of the most important domain is compute. This domain is for services that assist in executing custom code that you provide. Some examples are EC2 instances or Lambda. Even though there are several different services in this domain, all of them ultimately run on EC2 instances under the hood. The main differentiator for each is the level of abstraction and automation the service provides. Storage is another important domain that focuses on storing different types of data for retrieval at a later time. Specifically, this is going to be file system like storage. We're not talking about databases or cache here. S3 is the perfect example service for this domain, which is used to store just about anything these days. The next domain is database, and it's pretty self-explanatory. This domain includes managed SQL databases with relational database service and NoSQL data stores with DynamoDB. Elasticache is also included in this domain, even though it may be debatable whether it can be classified as a true database. Network and content delivery is a hugely important domain that is often hidden under the covers. The networking concerns of this domain manage how external users access and interact with your application, as well as how internal AWS resources interact with each other. CloudFront rounds out the content delivery aspect of this domain, providing your applications with a high-quality CDN to get your content to users faster than you may ever need to. The developer tools domain is full of services dedicated to the development process, such as source control and continuous integration. These services aren't for users to interact with, but really are focused on the developer experience side of AWS. Using these are optional though, so don't feel like you need to use any of these developer tools services if you're developing on AWS. Services that focus on the service management side are in the management and governance domain. These services focus on the creation and management of other services in AWS. A lot of these services are used more by DevOps engineers, but we will be using CloudWatch in this course. The security, identity, and compliance domain contains services that deal with managing secure access to your AWS account and individual services. IAM is the main service here as it manages and provides the policies that affect nearly every service in AWS. The analytics domain focuses on services that allow you to consume and process data in different ways. From services like Elastic MapReduce, which lets you process big data, to the Kinesis service, which provides streams that facilitate data transfer, any service focusing on dealing with internal data can be found here. The last domain we'll talk about is application integration, which is for services that provide integrations between other services in AWS. For instance, services like Simple Notification Service and Simple Queue Service provides ways for applications and services to communicate with each other inside AWS. Simple Workflow and Step Functions give developers ways to orchestrate applications inside AWS. And those are all the main AWS domains. There are a few more, but their relevance to this course and likely your job are minor enough that I'm leaving them out here. Now that you understand the AWS domains, keep them in mind when you're looking for a solution in your application. There may be a cool new service in a domain that you're concerned with, and it might just be the perfect solution for your problem. Amazon provides a few different ways to interact with their cloud. The web console is one of the first you'll interact with, and the CLI is probably the second, as you configure your local credentials. But the AWS SDK Software Development Kit is likely what you'll use most of the time in your role as a developer. This is because the AWS SDK provides the simplest interface between your code and the cloud. AWS distributes and maintains these SDKs in multiple languages so you can develop in the cloud in whatever language your application is built with. There's some other open source SDKs for languages that aren't supported already by AWS. These are typically very usable, but it's important to know when an SDK is officially supported so that you can understand the level of support it'll receive. Let's take a look at the official SDKs available from Amazon. First of all, AWS provides SDKs for the current most popular server-side development languages. In no particular order, these are Java, .NET, C++, Python, Ruby, Go, and Node. On the client side, you can use the same JavaScript SDK that is used with Node. On mobile, you have some interesting options. There are official SDKs for Android, iPhone, the Xamarin platform, and Unity. With all of these offerings, it's very likely that your language of choice has a fully supported SDK from Amazon. In this course, we're going to be working with an application built on Node, so we will be using the JavaScript SDK extensively. If you want to get a head start with it, here's the URL for the documentation site for the JavaScript AWS SDK. This course is designed to not only teach you how to be an amazing AWS developer, but also to help you complete the AWS Developer Associate exam. The exam tests your knowledge of AWS and the many different services, options, and problems that you encounter in the process of developing on the platform. The content of the exam is updated every few years, so while I can't make any assurances that this course will contain everything you'll need for the exam whenever you take it, I am covering each topic as if you'll be tested on it. The current AWS Developer Associate exam contains all multiple choice questions. Typically, each question will focus on a single service and ask about topics, service specifics, or service limits. There are also questions about debugging certain problems and giving architecture recommendations based on use cases. There's no real way to know which services will be on the exam, but the core services of AWS like EC2, S3, and DynamoDB are almost guaranteed to be on the exam. I've also seen services like SQS, Route53, and Elastic Beanstalk, to name a few. Bottom line, the more you work with and learn about AWS, the easier the test will be for you. I recommend watching all of the courses in the AWS Certified Developer path here on Pluralsight, and then continue building more projects. If there's a service you aren't very familiar with, it wouldn't be a bad idea to build something just to give it a shot. In addition, I've created a course called Demystifying the AWS Certified Developer Associate exam, which serves as a great intro to the exam. The course covers the exam format, how to study, which resources to use, and what the day of the exam will look like. I recommend watching it after you've completed the AWS Certified Developer path to put you on the best footing for the exam. In order for us to utilize a bunch of AWS services together, we need an application to work with. For this course, I provided a demo web application project that we'll modify to make the most of AWS. Here's the demo app called Hamster Ball Fantasy League. This site features a make-believe league of hamsters racing each other in hamster balls. The site is a single-page application built with React and Redux. The backend application is built with Node and the Happy Web Application Framework. With HBFL, you can look at individual hamster details to see how they've been faring. Look at race details to see what place each hamster came in. And also look at the leaderboards to see how each user is ranked based on their favorite hamsters. If you log into the application, you can get access to your own data and can pick and choose which hamsters you want to represent you in the leaderboards. You can only favorite 3 at a time. There are some behind-the-scenes controls in this configuration panel that let you reset the race results and start them again. These are all make-believe, randomly generated results, so each time you run the simulation, you'll get a different outcome. See if you can make it to first place. This application is going to utilize a multitude of different services to provide some robust capabilities for users. Starting in the next module, we'll get this application running in EC2 and see how it feels when it's served from the cloud. As we begin this course, I'll assume that you already have an AWS account set up. If you don't, pause the video and go sign up for one now. New accounts receive access to the free tier for 1 year, so you might just want to create a new account anyways for the purposes of this course. Now, one of the first things I like to do on a new account before I create any resources in AWS is to set up a billing alarm or an AWS budget. This lets you know once you've accrued a certain amount of charges on your account. It's a nice peace of mind in case you spin up some resources without being aware of the costs. I can say it has saved my bacon a few times. Billing alarms through CloudWatch used to be the main way that you could achieve this billing monitoring, but AWS introduced a budget service to provide more features and the ability to fine-tune the monitoring based on an incredible number of factors. We'll use it in a very simple way, but the functionality is there to use it in a more robust manner. Let's set one up. First, log into the AWS Management Console with the root user. This will be the email address that you first started the account with. Then navigate to the AWS Budgets dashboard. From this front page, click the Create a Budget button. If this is a new account, you might see an alert like this here that wants you to enable Cost Explorer on your account to open up new types of budgets. You can do this later. It won't hinder what we're doing since we're going to set up a cost budget, which is already selected here. So click Next. We'll start by looking at the Set Budget Amount section. We want to look at a monthly period since that's how we're billed by AWS. Then we'll have this budget be recurring, so it just continues to check every single month. The Start Month dropdown should already be populated with the current month, so you can leave that as it is. Now for the budget amount. I always set this to a small enough amount that it lets me know if I did something wrong. For instance, I left some resource running. Also, I set it low enough that I won't mind if I accidentally get charged for that amount. For those reasons, I pretty much always set this amount to $5. The budget scoping section is where you can put filters on the budget, such as which regions, services, or even tags to include. Your screen may look like mine, spinning, if you haven't enabled the Cost Explorer functionality yet. Continue on and give your budget a name, such as AWS Budget. Then you can click Next. Now we need to add an alert. This is when and how you'll be notified if the budget is exceeded. Click the Add an Alert Threshold button. First, we'll define the when of the notification. The threshold amount refers to the dollar amount we specified in the previous screen. I'm going to enter 100 here, so it'll let me know when the full amount will be exceeded. In the trigger dropdown, you can either choose actual, which means it'll be triggered when you actually have billable charges over that amount, which means you'll have to pay it, or forecasted, which means it'll be triggered when you are forecasted to have charges over that amount by the end of the month. This means that you can terminate those resources before they actually hit your budget amount, hopefully saving you some money. So choose forecasted. Next, add an email address to receive an email if the budget threshold is exceeded. Then you can click Next. Here you can add additional actions for the budget to trigger, such as terminating EC2 instances. But we're not going to do that, so just click Next. Now we can review the budget configuration and finally click Create Budget. And that's it for creating your budget. Now you'll be notified if any AWS charges sneak up on you. Before we start working with AWS, there are some prerequisites you'll need to ensure that you have completed. The first is to have the AWS CLI downloaded, installed, and configured with a user. The user should have permissions to do almost anything in AWS. If you have to be more restrictive than that, I recommend taking a look at the services in this course and just giving yourself read-write permissions only for those. We will be working a lot with the SDK, and it requires you to have your CLI level configuration already set up. Next, you should have a good code editor installed. I'll be using VS Code, which is a free editor from Microsoft. If you want to use something different, my only suggestion is to just make sure it has some syntax highlighting and auto indent. They're pretty essential for JavaScript development. You'll also need to have Node and NPM installed. You can download these from the Node website at nodejs.org. This is the version we'll be using in this course, so it's best to download a matching major version. Finally, make sure to download the demo project code. You can get this code in the exercise files section of this course on Pluralsight, but I'm also making it available on GitHub if you prefer to get it from there. I would say the benefit of using the exercise files from Pluralsight is that any changes in the course are present in that code from each module. There's a before and an after section of the code. It can be really beneficial to have that available just in case you make a typo during a lesson, and we will be writing a lot of code in this course. And that's all you need to get started. Now let's dive deeper into the world of Amazon Web Services. Welcome back to AWS Developer Designing and Developing. In this module, we're going to learn advanced methods for creating and managing Elastic Cloud Compute, or EC2, instances. In the previous Getting Started course, we saw how you can easily create instances using the AWS console. But in this course, we're going to interact mostly with AWS through the SDK and AWS CLI. So we'll be utilizing different methods to do some operations you may have learned in the past. We'll start the module by covering some of the fundamental concepts of EC2, AMI, and the AWS Marketplace. Then we'll discuss the EC2 REST API and look at the details that go into each request. I'll spare you the pain of manually making one of these requests because it is really inconvenient. Next, we'll create an EC2 instance with the SDK and install the demo application. With our instance created, we'll look at different ways to manage your EC2 instances with the SDK. Then we'll use an existing product from the AWS Marketplace to launch an instance that will have some pre-installed software on it. And with our instance created, we'll create an AMI from that existing instance to get a good reproducible image. Finally, we'll look at the limits of the EC2 service and AMIs. These limits are important to understand when designing your AWS solutions and should help you from painting yourself into a corner in the future. The EC2 service is one of the most fundamental services offered by AWS. It underpins many of the other services in AWS. We've already covered most of the basics of this service in the Getting Started course, so we're going to go into a bit more detail into EC2 in this course. The basic unit in EC2 is the instance. This is a virtual, not physical, self-contained computing unit. Each instance needs software installed on it to run, and this is available in AWS as an Amazon Machine Image, or AMI. AMIs can be a basic Linux or Windows operating system installation, or include other software like a vendor's application or some open source application. To give an example, later in this course we'll use an AMI that comes from the AWS Marketplace with Linux and Node.js pre-installed. You can create your own AMIs with your custom software installed or launch one from the AWS Marketplace. You can also create AMIs iteratively by launching an instance with an Amazon Linux AMI, then adding your own software and creating an AMI from that. AMIs are very flexible and versatile in that respect. AWS provides a separation between the instance's execution environment, such as the CPUs and memory available to the instance, and the instance's file storage. In Module 4, we'll cover this in more detail, but basically, EC2 gives you three options for how your EC2 instance file system will be managed. The first is instance store volumes. These are physically connected to the EC2 instance and act similar to basic hard drives. They can't be reused for other EC2 instances. The second option is elastic block storage, shortened to EBS. The main difference between EBS and instance store volumes is that EBS volumes can be connected to other instances and also can live on even if the instance is terminated. The third option is Elastic File System, shortened to EFS. EFS differs from EBS in that it is scalable in size. Other details such as a separate lifecycle from the EC2 instance and being able to connect to different instances is similar. When creating an AMI, you have the option to define an instance volume-backed AMI or an EBS-backed AMI. Choosing one or the other restricts what states are available to the created instance. An EBS-backed instance can be stopped for an arbitrary period of time. The instance data will be persisted on the EBS volume. Contrast this to an instance volume-backed instance, which can only be terminated or restarted. Can't be stopped. It's a small distinction, but it can afford quite a bit of flexibility with using EBS volumes. A larger distinction between the two types of instances is the boot up time. An EBS-backed instance created from an AMI is significantly faster to boot than an instance-backed volume. The main reason that EBS is faster is that the AMI data for an instance-backed volume must be transferred from S3 on boot up, which is different from EBS. EBS was introduced by AWS after instance store volumes, so there are many good reasons to use EBS. One more important detail of AMIs is the visibility of the image, basically who has permissions to use it. When creating the AMI, you will need to specify the launch permissions. Your options are public, which allows anyone to launch an instance from your AMI, explicit, which lets you give permission to certain AWS accounts to create instances from your AMI, and finally implicit, which only allows you to create instances from the AMI. You can also publish AMIs to the AWS Marketplace, but we won't be covering that in this course. There are a few high-level instance attributes that you have to decide on before starting an EC2 instance. One of them is instance type, which I covered in the Getting Started course. Another attribute is the instance class. These classes are spot instances, on-demand instances, or reserved instances. You may have seen these terms, but I'll define them here and give them a little more explanation. In this course and the Getting Started course, we're only using on-demand instances, but based on the descriptions, consider giving the other classes a try. Instance class doesn't have anything to do with what the instance can do. It really defines the conditions in which the instance lives and how much you'll pay for it. On-demand instances are the usual pay only for what you use, no commitment instances that we spin up and spin down like nothing. These instance types are good for applications that need to be scaled up and down. It's also the best kind of instance when you're learning AWS, like we are, because you can kill the instance when you're done playing with it. Reserved instances are just like they sound, where you make a commitment to AWS and reserve a set number of instances for a certain period of time. There are different lengths to the commitment time, typically between 1 and 3 years, but the discounts can be massive, some up to 75% off. If you're a stable company that will reliably need certain instances running for that period of time, reserved instances might be a great way to save some money. The final class of instances is called spot instances. These are instances that you bid on, and they utilize spare EC2 computing power. Think of it like the unused hotel rooms or airline seats that are sold at rock bottom prices at the last minute, just because it's better to get some money than no money. Discounts can be even deeper than with reserved instances, up to 90% off, but there's no real guarantee on availability. It's suggested that only extremely flexible compute jobs utilize spot instances. A web application is not a good use case for spot instances, but a research job or data processing job might be a good fit. AWS provides a REST API to perform operations on services in your account. Just like any typical REST API, it lets you perform normal CRUD operations, such as creating EC2 instances or listing all available AMIs. The API seems very convenient before you discover the signing procedure required for each request. When sending any API request to AWS, you must first sign the entire request with your AWS credentials and add the generated value as a query parameter. This is actually common with secure APIs, but can make it difficult to work with manually. AWS understands this can be difficult, which is why they develop and maintain the SDKs. Inside the code of the SDKs, AWS is signing each request made for you. Indeed, most of the SDK is just a thin layer of code over the REST APIs. Making a request to this REST API, especially signing that request, is a convoluted process I wouldn't wish on anyone. It's a process that requires multiple levels of hashing, creating HMACs, and then actually making the request. But let's go ahead and take a look at the process involved so we can appreciate what the SDK does for us. First of all, you need to decide which version of signature you want to produce. Version 2 is the older version, supported by many of the original services, but it's largely being deprecated in most places. Version 4 is the preferred signature version. Certain newer AWS regions actually only support version 4, as do many newer services. Each signature version has a different process when signing requests. Version 4 is the more secure and therefore more complicated process. With a version 4 signature, you'll start by creating a canonical request. This is a combination of the HTTP method, the URI path, query parameters, any headers, and finally, the hashed contents of the request payload. The next step is to create a string that will be signed for your request. This string contains the hashing algorithm used, the date, the region, the service, and finally the previously derived canonical request that has been hashed with SHA-256. And we're not done yet. Once we have this string, we need to actually sign it. To do this, we'll need to first calculate a signature by making several passes through an HMAC, and then finally signing our string with the resulting signing string. That process gives a signature, which we will add as a query parameter to the actual request when we make it. This process is pretty difficult to get right, as I myself experienced trying to manually sign a request. The errors when you get it wrong are unhelpful and the documentation is not the clearest. Luckily for you, me, and every other developer in the world, you can instead just use the AWS SDK to make these requests. You won't have to sign anything at all, it does it all for you. The SDK uses your local credentials to make the request and then return the response to you. Due to the complexities involved, I'm sure you'll be grateful that we'll be using the SDK as our sole interface to the AWS REST APIs for this course. In order to run your application in AWS, we need to have one or more EC2 instances to execute that code. So the first step is to create an EC2 instance. There are many different ways to do this. In the Getting Started course, we mostly use the AWS Management Console to create resources. And another great creation method is using the AWS CLI, which can be useful if you're doing automation. But we are going to use the AWS SDK to create an instance with code. And before we can create the instance, we need to create a few other resources. In this clip, we're going to create a security group for the instance. Then in the next clip, we'll create a key pair, and then finally, we'll use both and create the instance. The first change I want to make will have impacts across your entire project. Whenever we do things with the AWS SDK, we need to tell the code which region we want to use. You need to do this every time you perform an operation in your code, so I want to make that process simpler, where you don't need to type your region over and over and over. Open the .env file in the demo code. There's a string here which will be saved as an environment variable when you run your code. Modify the string to have the value of the region ID that you're using. Then save the file, and your region is set to go for the rest of the course. Now, a lot of this course will be using code to perform operations through AWS, so I've created a scripts folder in the course exercise files. This scripts folder is organized by module, so navigate to the module 03 folder. I've created a file we'll modify in this clip called create-ec2instance.js. This file provides a blueprint for the changes we need to make. Each modification has a to-do comment, so it's clear where you'll be making your modifications. I'll walk you through the file to start with. At the top are dependency imports. Then we've got two to-dos where we need to create a new EC2 client with our region and send a command. This is a convenience function, the send command function, that we'll use in the operations functions below it so that we don't have to write the same code multiple times, keeping our code dry. Next are some local variables being declared. Then we've got the code that calls several functions to create a security group, create a key pair, and then create an EC2 instance. Below that are three functions that we'll need to implement. The first one is to create that security group. The second is to create a key pair, and the last is to create an EC2 instance using the security group and the key pair that we just created. As a side note, an EC2 instance can be created through the SDK without an explicit security group or key pair. If neither are given, the instance is assigned the default security group in your account and no key pair is assigned. After the fact, you can reassign security groups, so getting the default one isn't much of an issue, but the key pair is more serious because if you're using an AMI that isn't pre-configured to allow a different type of access method, such as a password, then you won't be able to SSH into your instance if you don't start it with a key pair. With a vanilla AWS Linux instance, you must attach a key pair to access it like this. And let's cover one more thing. Version 3 of the JavaScript AWS SDK, which we will be using in this course, is pretty different from version 2. I want to cover those differences real quick. The first is how you import things. In version 2, you import the entire AWS SDK dependency. Version 3 is more modular, and it allows you to only import the code that you want to use. These are bundled into clients, such as the EC2 client in the dependency as shown here. In addition, when we import things from a client, we'll destructure the result and only import the constructor functions that we'll be using. These will usually be one client and several commands. This follows into the next big difference in version 3, how you make something happen in AWS. There's a new pattern that you'll be following. First, you instantiate a client. Then you instantiate a command. Then you use the client to send the command to AWS. This pattern happens over and over with the new AWS SDK. We'll be implementing a send command function in most of our files to keep our code dry, but just know that this client command send command pattern is the way things happen in the new version of the JavaScript AWS SDK. This new version doesn't apply to other AWS SDKs with other languages. Now let's get started with the changes in this file. After we've made all modifications and run this file, we will have a running EC2 instance with a security group allowing us access and a key pair that has been saved locally that we can use to access that instance. In addition, the EC2 instance will already have Node installed, the demo project downloaded, dependencies installed, and the demo running on port 3000. It's a lot of things. First, scroll to the top of the file at line 2. We need to import the EC2 client constructor to start with. Replace the comment with a const declaration and curly braces. In the curly braces, enter EC2 client entered as Pascal case. Then add an equals after the curly brace and require the @AWS SDK /client EC2 package. With our client, we can now implement the send command function. As I mentioned earlier, this will help us keep from repeating code. The function will take a command as an argument, create a new EC2 client, and then send the command with that client. So start by creating a new const variable called client. Assign to it a new constructor call of the EC2 client variable. Pass in an object literal with the property region and the value of process.env.aws_region, with AWS_region all being uppercased. This is how you'll define the region for the AWS SDK to use, which will use the region value that we modified in that env file. In the next line, we'll return a call to client.send, passing in the command variable. This is the pattern that I mentioned a bit ago. All right, now we can implement the create security group function. The first step is to create the input for our command. Create a new const variable called sgparams. Assign to it an object literal. In these params objects, which we will write many of, all the property keys will be Pascal case, starting with a capital letter, so keep that in mind as you add them. Add one property called description. The value will be the sgname parameter. Then add another property called group name, with the value as the same sgname parameter. Now we can instantiate our first command. To do this, we need to import it from the AWS SDK. Scroll to the top of this file and add a comma after the EC2 client import inside those destructuring curly braces. Now import the create security group command object here. Then scroll back to the code that we were writing. Add a const named create command. Assign to it a new constructor call of create security group command. Pass into that the sgparams object we created above. Now the command will have all the right instructions and details we want. Now we just need to use the client to send it, which is what our helper function above will do. In the next line, add a new const called data. Then after an equal sign, add the await keyword, and then call send command, passing in the create command variable. The send command function needs await here because it is an async function that returns a promise. Now once the command is sent, it'll create the security group and return the data about that security group. We will use that in our next step, which will be to set the rules for the security group. We want to set up two ingress rules. First, we'll want to enable port 22 so that we can SSH into the instance once it's been created, and then port 3000 so we can access the demo app in our browser. So start by creating a new const called rules params and assign an empty object literal to it. There are a few properties required to create these security group rules that should sound familiar to you if you've set one up with the management console before. The first is the group ID to apply the rule to. We can get that from the data variable populated by the creation command response. For the value here, enter data.groupID. The next property is IP permissions, which is an array. This array enables us to configure multiple rules in one request. Create an object in this array and add the property IP protocol. The possible values for this are protocols like TCP or UDP. Enter TCP here, all lowercase. The next two properties, from port and to port, define the port range you're enabling the rule for. In the first case, we'll enter the number 22 in both from port and to port, since we're allowing SSH here. Finally, add the property IP ranges with the value as an empty array. Here is where we can define who this rule applies to. Add an empty object with the property CIDR IP. We'll enable access to anyone, so give this property the value of 0.0.0.0/0. Now we need to also add the rule for port 3000. So copy this rule object, add a comma after it, and then paste. The only differences will be the from port and to port properties, and you can set both to 3000. Awesome. Now we're ready to send one more command. First, let's import it at the top of our file. After EC2 client, enter authorize security group ingress command. It's a long one. And then a comma. I like to organize these imports as the client on top and then the commands that are in alphabetical order below it. That's why I put the authorize command before the create command here. Now we can use the command, create a new const called auth command, and then assign to it a new constructor call of authorize security group ingress command, passing in the rules params variable. Then we just need to send it. In the next line, add the return keyword and then call send command, passing in auth command. And with that code complete, we've successfully written the code to create and assign rules to a security group. In the next video, we'll create the key pair. In this video, we're going to continue our work from the last clip and create a key pair for an EC2 instance using the AWS SDK. This create key pair function is what we'll need to implement. So let's get started. First, create a new const variable named params and assign to it an empty object literal. A key pair only really needs one property to be created, which makes it really easy for us. The property identifier is keyname, and you can give it the value of the keyname argument that was passed into the function. Now we need to create the command. To do that, we need to import a new command constructor at the top of the file. Make a new line after the authorize command and add create key pair command and a comma. Now back in the function implementation, create a new const variable named command and assign to it a new constructor call for create key pair command, passing in the params variable. Now we just need to send that command. In the next line, add the return keyword and then call send command, passing in the command variable. Returning this function call here is important because when the key pair is created in AWS, the function returns the contents of that key pair's private key. If you don't save this locally, the key pair is essentially useless. I provided a helper function that will actually take this key pair data and save it locally as a file. If you don't return the send command response here, it'll basically throw away the created key pair, which you don't want. Now the code to create the key pair is complete. If you scroll up, you'll see the key pair persistence being called after the key pair is created. This is where it will save the key pair locally in your SSH folder. In the next clip, we'll take the work that we've done creating the security group and the key pair, and we'll create an EC2 instance using both. We've created a security group and a key pair, so now we're ready to create an EC2 instance that uses both of those resources. We've only got one unimplemented function left in our file, create instance. This function takes the arguments sgname and keyname, which were used to create the other resources. Inside this function, we'll start by defining a params const variable and assigning an empty object to it. As you can probably imagine, this params object will have many more properties than the other ones that we've used. The first property to add is image ID. This is the AMI ID that will be used to create the instance. And to get this, we'll need to make a little side trip to the AWS Management Console. See, there are a couple of interesting things about AMIs. First, there's a command in the EC2 client in the AWS SDK called describe images command that can be used to essentially search for AMIs that you can create instances from. The problem is searching with no filters takes a super long time, and it's just easier to go to the AWS Management Console directly if you know what you're looking for. The second thing to know about AMIs is that they are region specific. For instance, an Amazon Linux 2 AMI will have different IDs depending on which region they're in. And you can't just reference the ID from one region to create an instance in a different region. The image IDs are unique for each region, even if the image contents are the same. So for that reason, I'm going to show you how to find the AMI ID that you'll use in your code. Go to the EC2 dashboard in the AWS Management Console. Click on the Launch Instance button and then Launch Instance. And you'll be presented with the AMI selection screen. At the top, there's the Amazon Linux 2 AMI. At the end of that title is the ID. The ID you see probably won't match this one, since you may be using a different region or they might have published an update. There will also be two different IDs, one for x86 and one for ARM. These are AMIs for different types of EC2 instance architecture. We'll be using a T2 micro instance, which is based on x86 architecture, so copy the AMI ID for x86. Now switch back to your code and paste that in a string as the value for the image ID property. The next property in params is instance type. This is a type of instance such as T2 small or M4 extra large and defines the properties of the instance. We've talked before about what these mean, and we can use one of the smallest here, T2 micro. Next, we'll define the key pair name with the property keyname and enter the value of keyname from the function arguments. Next is the max count property, which defines how many instances to create. Enter 1. Then we have the min count property, and you can enter 1 again here. Now add the property security groups and give it an array as the value. This is where we can add any security groups to the instance. Enter the sgname argument into the array. You can add more than one security group here if you want to. There's also a security groups ID property that you could use instead and reference these security groups by their IDs rather than by their names. But since we already have the name argument, it's just easier to do that. The last property in our params object is user data. User data has a couple of different uses with EC2 instances, but we will use it to run shell commands once the instance starts. If you open the file in the O3 folder called ec2 startup.sh, you'll see several shell script commands. These commands will install node and git, clone the demo project from my GitHub, install the dependencies, and then run the demo project. You can't just put these shell scripts directly into the user data field. It needs to be base 64 encoded. So I've gone ahead and encoded these commands for you in this comment below. So copy that line without the preceding hash symbol. Then go back to the create EC2 instance file and paste it into a string as the user data value. And with that, we have all the params in place. Next, we need to build our command. Scroll to the top of the file so we can import the constructor. After the create security group command, add a comma and then add run instances command. Then go back to your function and create a new const variable called command. Assign to it a new constructor call of run instances command, and then pass in the params variable. The last step is to send the command, so return a call to send command, passing in the command variable. And with that, we've completed our script. Now for the fun part, running it. But before that, how about a PSA? This code is going to assume two things about the region that you're deploying to. First, it's assuming that you already have a default VPC for that region. For some regions, AWS will configure this by default, and for others, it won't. If you look at the EC2 dashboard in the management console, AWS has the default VPC listed. If you don't have an ID here, then the default VPC isn't configured for this region in your account. On this page, AWS has information and the steps for creating that default VPC manually, so make sure to follow those steps before running the script if you don't have a default VPC already configured for your region. The other thing this code assumes is that the subnets in your default VPC are configured to auto-assign public IPv4 addresses. This means that when you create a new instance in these subnets, they will give the instance a public IP address. Now, most default VPCs and subnets already have this configuration set up, but you might want to check by looking at this configuration detail in the default subnets to make sure it's already configured correctly. Now move over to your command line and navigate to the demo project. We haven't installed dependencies yet, and we'll need them for our script. So go ahead and run npm install at the demo project root. Once that completes, navigate down to where these scripts resides. Now you can run node create ec2 instance.js to execute that script. No other arguments. After a few seconds of processing, it should print out the location of the key that was written locally and the details of the instance that was just created, or maybe an error if something went wrong. The actual boot up of the instance can take a few minutes, and it's done completely on the instance. You don't see any output here. I'm going to go ahead and fast forward the video, and then I'm going to refresh the EC2 instance dashboard in the console. Here's the instance that was created. And because it's running, and because at this point the demo application should have already started working, if you copy the public IP address, which is found here, open it in a new tab and add :3000, you should see Hamster Ball Fantasy League running completely in AWS. In the next clip, we're going to look at what we can do with this instance now that it's already been created. Once your instance has been created, there are a few different operations that you can perform on the instance as you manage its lifecycle. The SDK command that you'll want to use to modify the configuration of a running instance is modify instance attribute command. Some examples of instance attributes this command allows you to modify are granular ones like kernel and RAM disk, and higher level attributes like instance types and block device mapping. I really didn't think there was enough for us to dig into with this command, so I thought we'd actually try out 2 different commands to manage existing instances in this video. Just wanted to mention this modify instance attribute command in the beginning here. The describe instances command is useful because it will list all the instances you currently have running in a given region. You can apply different filters to further filter the query and limit what types of instances are returned. I wanted us to give this command a try and see the type of response we get. In your code editor, open the file manage-ec2instance.js. We can start by importing the EC2 client and the describe instances command. At the top of the file, replace the to-do with a const variable with curly braces. Inside the curly braces, first enter EC2 client, and then under that, add the describe instances command. Then add an equals after the curly brace and require the @AWS SDK/client EC2 package. Now let's implement the list instances function. The describe instances command only has a few possible parameters in the command input. The main one is the filters to apply. You can filter based on things like instance type, VPC ID, or tag. For our purposes, we're not going to use a filter, but I just want you to know that that functionality exists. So we can go ahead and declare a new const variable named command. Then assign to that a new constructor call of describe instances command. Even though we aren't providing any properties to this command, it still requires an object as input. So just pass in curly braces to the constructor call. Then in the next line, just return a call to the send command function, passing in the command variable. If you scroll to the bottom of the file, the list instances function is called and the result logged to the console. We'll add a little more to the list instances function, but I wanted us to go ahead and run it and see what kind of output we got. On a command line, make sure you're in the right folder and then execute node manage ec2 instance.js. Once it's finished running, it should print out a bunch of JSON to your console. This is the structure of the data object that is returned once you've sent the describe instances command. The property that we care about here from this JSON is called reservations. A reservation in this context is essentially a request from some user to AWS to launch an EC2 instance. The request could have come from the management console, the SDK, the command line, or even something automated like an auto-scaling group. If you have more than one instance on your account, there is a very high possibility that the array that is assigned to the reservations property will have more than one object in it. In my case, there's only one because I'm on a new account. Each of the objects in this reservations array has an instances array. This is the information that we actually want. The actual instance info is hidden here just because the JSON printout doesn't go that deep. So let's go back to the code to reduce the JSON that's coming back. We're going to use a little JavaScripting to join together all the instance arrays from each reservation object. So just stick with me here. First, replace the return statement at the end of list instances with a new const variable named data. Then add the await keyword before the send command function call. In the next line, we'll manipulate the data object. So enter the return keyword. Then enter data.reservations, and then chain a call to reduce. Inside this function call, you'll create a new arrow function with 2 arguments, I and R. I is the aggregated instances array, and R is the current reservation object. Inside that function, return a call to i.concat, passing in r.instances with a capital I. Then, after the closing curly braces, add a comma and then an empty array, which is the seed that our reduce function requires. Now, if we save that and go back to the command line and execute node manage ec2 instance.js again, we will see all the instance information output. You've got a ton of information here, like the instance type, the key name, the public IP address, And if you've got more than one instance, you should see them all listed here. We'll use a piece of the information here with our next management function. So let's go ahead and grab it. Find the instance you just launched from the create EC2 instance script. The easiest way to identify that would likely be the key name that should show hamster_key. Copy the instance ID property, which will be like a lowercase I, hyphen, and then a bunch of letters and numbers. Switch over to your code editor and paste this instance ID into the parentheses of the terminate instance function call at the end of the file. Ensure that there are quotes around the ID in case you didn't copy them. Now let's implement terminate instance. This function is going to take an instance ID as an argument and tell AWS to terminate that instance. For the record, you can also stop an instance if you want to. The key difference between stopping and terminating an instance is that a stopped instance can be restarted, but a terminated instance can't. We will need a params object to pass into our command, so first declare a params const object. It will only take one property, instance IDs, which is an array. You can terminate multiple EC2 instances with a single command, which is why this is an array. Inside this array, just enter the instance ID argument variable. Now we'll import the command we need. So at the top of the file, add a comma after describe instances command and add terminate instances command. Then back in our function, create a new const called command and assign to it a new constructor call of terminate instances command, passing in the params object. We won't modify the response from the command at all, so in the next line, just return a call to send command, passing in the command variable. I've already written the code to execute this function at the bottom of the file, but as you saw earlier, it's currently commented out. So comment the line with the list instances function call, and then uncomment the line below it calling terminate instances. Save the file and then switch over to your command line. We're going to terminate our hamster instance by running node manage ec2 instance.js. When the script is complete, it'll output the response from the terminate command, which should contain that same instance ID that was passed in. And that's it for terminating instances. If you don't trust your command line, you can go check the AWS Management Console and see that the instance in question is currently shutting down. In the next clip, we're going to launch an instance with an AMI from the AWS Marketplace. Running your own code on a vanilla Linux or Windows instance is one of the most common use cases for EC2, but occasionally there is some vendor-provided software that you want to run as well. You could install this yourself, but you'll often find that there is an existing AMI with the software pre-installed available on the AWS Marketplace. Let's take a look at the Marketplace by navigating to the EC2 dashboard in the AWS Management Console. Click on the Launch Instance button and then Launch Instance, and you will be on the AMI selection page. The software that are available from the AWS Marketplace are just Amazon machine images with an operating system and some custom software pre-installed. That's basically it. On the left-hand menu, click AWS Marketplace, and here you'll be able to see what's on offer. There are some featured and popular AMIs, and then a bunch of categories. You can see there's quite a few categories available. Thousands of AMIs in them, in fact. For this course, I wanted us to launch an instance with an AMI from the Marketplace, specifically one that has Node already installed on it. In the search box, type node.js and hit enter. There should be quite a few results, but look for the result titled Node packaged by Bitnami, and it should have a fairly recent updated by date. This number here is the version of Node that is installed on the instance. There shouldn't be any cost information here. If an AMI from the Marketplace does cost money, it will have the per hour cost listed next to the image information. You may see some other entries with a cost associated with it. Node is free and open source, and the Bitnami AMI is free as well. You'll still be charged for any instance costs, but the AMI has no additional charges. Now click More Info, and then click on the link ending in Product Detail page on AWS Marketplace. See, we're not going to use the console to launch this image, but instead grab the AMI ID and then use our scripts again. This next page has a lot more information about the image if you want to read it. For our current case, click this Continue to Subscribe button on the right-hand side. Now we're in the subscription page. We have to subscribe to this image, meaning that we must accept the terms and conditions. If this image had a cost associated with it, we would also be agreeing to pay whatever amount the image costs. Once you've looked at the terms and conditions, click the Accept Terms button, and then wait a while they process the subscription. I actually don't know why this takes any time at all, but it does. A couple minutes at least. So I'm going to fast forward, and then once the subscription has gone through, your page should look like mine, with a Continue to Configuration button in the top right. So click that now. Now we can finally get the AMI ID. You can adjust some parameters here, such as the architecture, version of node, and region. If you remember, I mentioned before, each AMI is region specific. This is why picking the correct region here matters. It's technically the same code on the AMI for each region, the same image, but the IDs are different based on the region. So even though everything should be automatically populated for you based on the region in your console, just make sure that your region is matching where you want to deploy it to. And then also make sure that the version of node matches what we're using in the demo project so far. You can see in the drop down that there are many different versions, major versions of node that you can choose from. Now, once you've selected everything correctly, copy the AMI ID that is displayed right here. And then switch back over to your code editor and open the create EC2 instance.js file. We're going to launch an instance using this AMI instead of the vanilla Amazon Linux AMI that we did before. So scroll down to the create instance function and paste over the image ID value with the AMI ID that you copied. Now we could run this just as it is now, but there are two more changes that we need to make. The user data we have here installs Node and Git, and then it clones the demo down and it runs it. We don't need to install Node anymore because this Bitnami AMI comes with it. So let's change this user data. Open up the file titled marketplace ec2 startup.sh. This is basically the same as before, minus the Node installation steps and the Linux package manager updated to apt-get, since the Bitnami image is Debian based. Copy the base64 encoded text minus the starting hash at the bottom and paste that into the user data string value in the create EC2 instance file. The next modification is to the key pair and security group names on lines 17 and 18. If we were to run this file again, it would try to create new resources with those names and then error out because they already exist. Let's give them new unique names by just tacking on a 2 to the end of each string. Now save the file, then switch over to your command line and run the file with node create ec2 instance.js. You should see the same type of message as when you ran the file previously. This time, however, you've launched the instance with a whole different AMI. I'm going to skip the video ahead in time a bit and then confirm that the instance creation worked correctly. I'll copy the public IP from that newly created instance into my browser and add the port 3000. And there's Hamster Ball Fantasy League. It's running on a new marketplace AMI that has Node pre-installed. In the next clip, we're going to create our own AMI from this instance. Amazon machine images are sort of like the primer for every painting that you want to create with an EC2 instance. It's the starting point and the base software that you build off of. But they do have another use, which is to help you easily reproduce an instance with your given application loaded on it. There are a million other uses for AMIs, but bottom line is that they are ubiquitous and super important throughout AWS. In this module, we're going to use the SDK to create an AMI from the instance we started up in the last clip. To do this, move over to your code editor and open the file createami.js. You can probably tell just from looking at the file, but there will be significantly less code than the last few files we worked on. We can start by importing the EC2 client and the create image command. At the top of the file, replace the to-do with a const variable with curly braces. Inside the curly braces, first enter EC2 client, and then after that, add create image command. Then add an equals after the curly brace and require the @AWS SDK /client EC2 package. Now on line 12, we're calling our create image function, passing in an instance ID and a name for the image. Once it's done, it just prints out complete. Nothing special. We'll go get the real instance ID to enter here later. Let's implement the create image function. We'll start by creating our params const object first. There are only a few parameters that the image creation operation needs. First is the instance ID property, which you can assign the function argument seed instance ID. Every AMI needs an instance to be based off of. This instance ID is what should be copied to a new image. Next is the name property, to which you can assign the image name argument. This name is basically just an identifier for the AMI, and that's it for the parameters. Now we can use this params object to send a create image command. First, add a new const with the identifier command and assign to it a new constructor call of create image command, passing in the params object. Then in the next line, add the return keyword and call send command, passing in the command variable. And that's it for implementing create image. One note on the create image function: it will create an image that is private, meaning only your account can launch instances with this image. To change the visibility of this image, you would use the modify image attribute command after the image has been created, or you can modify it in the console or with the CLI. The last step is to get the instance ID that we want to create our image from. We can use the manage EC2 instance file to do this. Open the file and make sure the list instances operation is uncommented and not terminate instances. We don't need to terminate anything. Then save that file and then move over to your command line and run node manage EC2 instance.js. You should have some instances output. In case that you are just barreling through this course, you may see both the instance we just created from the AWS Marketplace and the one that we had previously terminated with the Amazon Linux on it. If so, look for this state property. One of the instances should show as running, while the other should show as terminated. Copy the instance ID for the instance that shows that it's running. Now move back to your code editor and open up that createami.js file. On line 12 where it says instance ID, paste over that with the copied instance ID from the command line. And finally, save the file. Now we're ready to create our AMI. Move back over to the command line and run node createami.js. It should process for a second or so and then print out complete, meaning that it's done. You can go to the EC2 dashboard in your browser and then to AMIs in the menu to see the image that you just created. One thing I want to mention before we finish this clip is that even though you've created this image, the user data startup script that we were using doesn't actually attach to that image. This means that even if you start a new instance with the image that we just created, the demo project won't be started when the instance is created. The code for the demo project will be present on the instance, it just won't run. Reproducible user data would exist in a launch template, and that's what we're going to be talking about in the next module. All services and resources in AWS have limits. It's important to be aware of them so that they don't trip you up when designing AWS architecture. And that's the worst thing about limits. You end up hitting them at the most inopportune times. So let's take a look at some of the limits involved with EC2 and AMIs. EC2 has a limit on the max number of running instances per region. This actually gets a little complicated though, so I'll show you where to view these limits. Go to the EC2 dashboard in the AWS console. On the left-hand menu, there is a limits entry, and click on it. You'll see there are a lot of limits here, and they get very specific. They're also instance type specific, so you can really do a lot of damage if you get creative with the image types you're using. Scrolling down, you can see there are a few other types of limits listed here beyond running instance limits. One important thing to notice about all of these limits, though, is that you can select any of these limits and use the Request Limit Increase button. This means that these aren't hard limits. You can ask AWS to raise them if you ever need to. If you're using AWS with a corporate account or for your company, then raising these limits is rarely an issue. This page largely contains all the EC2 limits. As for AMI limits, we've already discussed that AMIs are region specific, so definitely keep that in mind. There doesn't appear to be a limit to the number of AMIs specifically that you can have, but since each AMI is stored using an EBS snapshot, and there is a limit of 10,000 EBS snapshots, I would assume the max number of AMIs you can have is 10,000. Also keep in mind that you do have to pay per EBS snapshot, so having 10,000 AMIs is not going to be cheap. We've taken a good tour of what EC2 has to offer, so you should have a good understanding of how computing works in AWS. Let's recap what we covered in this module. We started by discussing some specifics of EC2 instances, instance storage, and AMIs. Then we talked about the different classes of EC2, like spot instances, reserved instances, and on-demand instances, which is what we're using. After that, I walked you through how the signing process happens when making a request to the AWS REST API. And luckily, we don't need to manually do that since we're using the SDK. Then we started writing code as we created a security group, a key pair, and finally an EC2 instance. Once we had that instance, we looked at other SDK functions like listing instances and terminating instances. Then we took a trip to the AWS Marketplace to pick up an AMI preloaded with Node. And finally, we created an AMI from an instance that we can use when creating other instances. Hello there, and welcome back to AWS Developer Designing and Developing. This module is all about scaling computing, and we're going to look at two of the major tools to automatically scale your instances. Scaling is about meeting the demands on your resources without you having to stay awake all night. In order to achieve this magic, we'll first take a look at what scalability and elasticity mean within AWS. With this knowledge, we'll then take the first step by creating a launch template that describes the application instance we want to run. Then we'll create a load balancer that will handle and distribute incoming HTTP requests. Both the launch template and load balancer are needed for us to create the main scaling resource, which is an auto-scaling group. And the last coding step we'll need is to configure a scaling policy on that auto-scaling group. With those four pieces in place, our scaling configuration will be complete. We'll close out the module by looking at limits that exist with auto-scaling and elastic load balancing. Now let the scaling begin. In the world of the cloud and AWS, terms such as scalability and elasticity are thrown around like they're the most common things in the world. The terms are often used interchangeably, something which I'm guilty of as well. I've found, however, that the nuances of these terms often aren't completely understood and can result in some confusion in how each impacts your cloud architecture with AWS. In this clip, we're going to talk about each one in detail. Scalability in terms of AWS refers to the ability for your resources to increase or decrease in size or quantity. There's a lot of infrastructure involved to make something like this happen, so it's no easy task. Many of the services in AWS are scalable by default, which is one of the reasons that AWS is so successful. Scalability is pretty simple to define, which is why some of the aspects of elasticity are often attributed to it. Elasticity is the ability for your resources to scale in response to stated criteria, often CloudWatch rules. This is what happens when a load balancer adds instances whenever a web application gets a lot of traffic. Scalability is required for elasticity, but not the other way around. Not all AWS services support elasticity, and even those that do often need to be configured in a certain way. It might seem redundant, but the services in AWS that start with Elastic often support elasticity. Scalability gives you the ability to increase or decrease your resources, and elasticity lets those operations happen automatically according to configured rules. Together, they let you sleep soundly at night with the assurance that your applications are healthy no matter the situation. Now, in the next clip, we're going to start our path towards elasticity by creating a launch configuration. In the last module, I mentioned launch templates and how they are the place that you'll persist your user data. It's true, a launch template is the blueprint for automatically creating new instances. It contains all the key attributes for how to create an instance, including the AMI to use, the instance type, instance security groups, and the startup user data. Although they do stand alone, and you can actually manually create new instances just directly from a launch template, they're also a key component in an auto-scaling group. Before AWS created launch templates, auto-scaling groups used launch configurations to launch instances. You can still use launch configurations for auto-scaling groups, but launch templates give you one huge key advantage, and that's the ability to create new versions of the same template. Launch configurations weren't versionable, so anytime you made a really small change, a completely new launch configuration had to be created. With launch templates, you can create a new version if you need to update any of the configuration detail, and then you can just update the version through using tags on the launch template, or you can manually specify a version in your auto-scaling group. It is a much cleaner and more modern way to define your instance configuration. Let's create a launch template for our demo project. Go to your code editor and open the 04 folder in the scripts directory. We'll be modifying the create launch template.js file. This script is pretty simple with only one function that we need to implement. Also, since we've already gotten our feet wet with the AWS SDK, I'm actually utilizing a lot more helper functions here, so you can write less code and focus more on the important stuff. For instance, I've already imported the create launch template command here from the EC2 client. Also, you may have noticed that there is no EC2 client constructor being imported here. That's because I've already done that and implemented a send command function in the helpers.js file. In the execute function, you can see that we're also using a create IAM role function from that same helpers file, another one that I've already implemented for you. It's actually one thing that we need for the launch template that we haven't really talked about yet, an IAM role to give the EC2 instances permission to talk to other services in AWS. Here we are creating a role for the hamster instances. An EC2 profile is also created with this function, and the role is then attached to that EC2 profile. And then the ARN for the profile is returned from this function. The profile ARN will be added to the configuration for the launch template so that any instances that are created with it will use that profile. Be aware this role that the profile is using gives the instance administrator access to your entire AWS account. Just for simplicity's sake for the demo, when you're doing this thing for real, make sure that you never give any instance admin access in a production account. Restrict the permissions in the role to only the operations and resources the application on the instance actually needs. Now we can implement the create launch template function, so let's do that. We'll start by declaring a params const object. The first property is launch template name. Give it the value LT name. Next is launch template data, which has the value of an object. All the rest of the configuration for this params object will be in this launch template data object. The first property here will be IAM instance profile with the value of an object. Inside this object, there's only one property needed, which is ARN, and the value for this will be the profile ARN variable. Then that's it for that IAM instance profile object. The next property is image ID, which is the AMI that we want to launch from. We'll use the AMI that we created in the last module, but we do need to go get the ID for it. So to do that, switch over to the EC2 dashboard in the AWS Management Console and click on the AMI's menu option on the left. Find the image with the name hamster image and copy the AMI ID. Bring that back to your code and paste it as a string as the value to image ID. The next property is instance type, which is the EC2 instance type. I'll just enter t2.micro here, since it's cheap and what we've been using so far. Any instance type could be entered here. Next, add the property keyname, which will be the name of the key pair the instance will be launched with, and give it the value of the keyname variable. Now add a security groups property and set the value to an array. These security groups define the security groups that will be added to each instance that is created. In this case, we'll use the security group that we created in the last module, which is already declared here in the sgname variable, so add that to the array. The last property is user data. Since we're launching from an AMI built off the Bitnami AMI, open up the marketplace EC2 startup.sh file in the scripts 03 folder and copy the base64 string at the end. Paste that as a string as the value to user data. And that's it for the launch template configuration. Now let's create the command to create the launch template. In the next line, create a new const called command. Assign to it a new constructor call of create launch template command, passing in the params variable as an argument. Then in the next line, we can send the command, add the return keyword, and then call helpers.sendCommand, passing in the command. And that completes the modifications needed for this file. We can now run this file to create the launch template, even though the other pieces of our scaling architecture aren't ready yet. In your command line, make sure you're in the scripts/04 folder and run node create launch template.js. After a bit, the launch template details should be output to your command line, and that's it. In the next clip, we're going to create a load balancer as the next piece of our scaling architecture. A load balancer is an essential point for any elastic web application, establishing a single entry point for web requests that can handle any size load. Let's create our load balancer by modifying the file create-load-balancer.js in our scripts folder. Just like before, I've already implemented some of the support code so that you can focus on the actual load balancer creation. As we modify this file, I'm going to explain what I've already done so that you can kind of understand it at a high level. At the top, I've already imported two commands for creating target groups and creating listeners. This time, the client that we're using is actually different from the EC2 one. This client is the Elastic Load Balancing v2 client. Both of these commands are used in functions that I've already implemented below. We will be using another command for creating the load balancer, so let's go ahead and import that now. Under the create listener command, add create load balancer command. And don't forget the comma after it. Now in the variables section, you can see there are two variables that we need to modify. The first is the VPC ID for your default VPC. Since the load balancer will be created in a VPC, we need to give it that information to use. Move to the AWS Management Console and go to the VPC dashboard. We'll get the VPC ID first by clicking on Your VPCs in the left-hand menu. You'll likely only have one VPC, so copy the ID for it. In your code editor, paste that value in the string after the variable named VPC ID. Now go back to the Management Console and click on the Subnets menu entry. We need at least two subnets for the load balancer, and they need to be in the VPC that we just pasted. I don't have any additional subnets, but you can use this VPC column to make sure that you're choosing the right ones. I'm going to use the subnets that are in US East 2A and US East 2B, which I can identify using this availability zone configuration detail. When we're setting up the auto-scaling group, I'll use those two availability zones, which is why I want to choose a load balancer subnets to match that. Now copy each one of the subnet IDs and paste them into the subnet array as strings. Great. Just like the other script files, this execute function calls the operation functions that we are implementing. It starts by creating a new security group for the load balancer that is open on port 80. This is so that users can access the load balancer over HTTP from their web browsers. Then a target group is created and a load balancer. I'll explain the target group in just a second. The responses from each of those calls are stored in variables so that we can then get the ARNs for the target group and load balancer. Then a listener is created with those values, which connects the load balancer and the target group. I want to explain the relationship of all these different resources quickly. A load balancer is in charge of responding to HTTP requests and sending them somewhere. A target group is the destination defined where a load balancer will send those requests. This is going to be connected to our auto-scaling group and will basically end up being a group of EC2 instances with our demo project running on them. The listener defines a relationship between the two. In our case, the load balancer will be listening on port 80, which is for HTTP, and our target group will be listening on port 3000 since that's what our demo application is using. The listener will facilitate sending those requests between the two ports. Now let's implement the create load balancer function. Start by creating a params const object. The first property will be name, which you can give the value lbname. Then add the security groups property, which will define the security groups in the load balancer itself. Set the value as an array with just one value, the variable sgid. Next, add a property named subnets. Set this property to the variable subnets, which we populated earlier. Then add a property named type and give it the value of application as a string. The default value for this property is actually application, but I like to make it explicit so that you can clearly differentiate it from other types of load balancers. Now we can create our command. On the next line, add a new const called command. Assign to it a new constructor call of create load balancer command, passing in params as the argument. Then in the next line, add the return keyword. And then call helpers.sendELB command, passing in command. This send function is different from the one that we used before because it is going to be using a different client to send the command, the Elastic Load Balancing v2 client. I've already implemented the send function with that client. This function just has a different name. And that's all we need to modify. Below this function are functions to create the target group and the listener, and no modifications are needed for them. So now we can run this file. Move over to your command line and execute the command node create load balancer.js. There should be some output. Specifically, I want to draw your attention to the line that says target group name ARN, basically because we will need this in the next clip. So you can either leave your command prompt output alone, don't delete it, or you can copy this ARN and save it somewhere like I'm going to do. And with this, we have a load balancer ready to distribute web requests to instances. In the next clip, we're going to create an auto-scaling group that will create those instances. Auto-scaling groups are responsible for creating and removing EC2 instances from a group according to configured rules. They use a launch template when creating the instance, and they can be attached to a target group so that each instance can be used with the load balancer. Let's create our auto-scaling group. Open the file createautoscaling.js. Just like the other files, you'll see that I've already imported some commands for you, this time from the auto-scaling client. I've also implemented a special send command function for the auto-scaling commands, which I'm importing from the helpers file here. Now replace the value of the string for tgrn with the target group ARN that we copied from the command line in the last clip. You do still have that saved to your clipboard, right? Well, if not, you can easily get it from the management console right here. Now we can move on to implementing the create autoscaling group function. Start by declaring our params const object. The first property is autoscaling group name, which identifies this autoscaling group in the management console. Enter the argument ASG name as the value here. Next, add the property availability zones and set the value as an array. These are the availability zones where the autoscaling group will launch the instances. At least 2 need to be defined. These availability zones should match the subnets that we used in the load balancer so that the autoscaling group doesn't create an instance that can't attach to the load balancer. I'll enter US EC2A and US EC2B. The next property is launch template. Give it the value of an object. That object just has one property, launch template name, which can be assigned the value of the LTName argument. This is how the launch template that we created is going to be connected to the autoscaling group. When the autoscaling group needs to create a new instance, it'll use the configuration that's saved in this launch template to create the instance. And remember that launch templates are versioned. If we don't explicitly define a version here, then the autoscaling group will use the version that's tagged default on the launch template. You can update which number version is tagged default on the launch template by just modifying the launch template. Currently, version 1 is tagged default on our launch template because that's the only version that exists. Next, add the property max size, which defines the maximum number of instances to create. I'll enter 2. Then add the property min size, which defines the minimum number of instances to have in the group. I'll enter 1 here. The next property will be target group ARNs with the value of an array. Enter the TGARN variable, which we configured earlier. This property ties the autoscaling group to the target group. Now we can create the command. On the next line, create a new const variable named command and assign to it a new constructor call of create autoscaling group command, passing in params. In the next line, add the return keyword and call send autoscaling command, passing in the command variable. And that's all that's needed to create an autoscaling group. Now we're done with the autoscaling group creation code, but we're not actually going to run this file until we've completed the attachment of the autoscaling policy code, and we're going to do that in the next clip. So see you there. An autoscaling policy defines when an autoscaling group should scale up or down. And there are a few different types of autoscaling policies. Simple scaling policies are the original way that autoscaling groups worked. These used a CloudWatch alarm to monitor certain attributes and then perform an action once the alarm actually occurs. Only one action could be configured per alarm. Therefore, if you wanted true elasticity, you needed a policy for scaling up and a policy for scaling down. Step scaling policies were added as a way to define multiple actions when a single alarm fires. This allows you to modify the behavior of a policy based on the severity of the alarm that's being fired. The policy will keep scaling even after it's been initiated, which differs from simple scaling policies. The newest scaling policy, and my favorite, is target tracking policy. It's what we're going to be using. Target tracking policies allow you to just define a target for a metric attribute, and the single policy will take care of scaling up or down to stay pretty much right at that threshold. It's the easiest policy. It's kind of like a set it and forget it type operation, and it is what Amazon suggests you to use now for autoscaling groups. In our code editor, back in that create autoscaling JS file, we're going to implement the create ASG policy function. To start with, we need a params const object, so go ahead and create that. We're going to be putting all of our policy details in here. The first property is adjustment type, And this defines what the policy should do. Enter the string change in capacity here. The next property is auto-scaling group name, and you can set the value to the ASGName function argument. Next, add the property policy name, which is just the unique identifier for the policy. You can set the value to the policy name function argument. The next property is policy type. Enter the string target tracking scaling. Other options for this are simple or step, which I explained earlier. Next, add the property target tracking configuration and set the value to an object. These are the details about what metric to use. The first property for this object is target value. We're going to be watching CPU, so if you enter the number 5, then the auto-scaling group will scale up and add instances if it's above 5% CPU utilization, or it'll scale down and remove instances if the average falls below. So enter the number 5 here. The next property is predefined metric specification, and give it an object as a value. This object has one property, predefined metric type, with the value of a string with the text ASG average CPU utilization. Because CPU utilization is a predefined metric and it's well understood by auto-scaling groups, this is how we can use it. And it's going to average the CPU utilization across all of the instances in the auto-scaling group. After the params object, create a new const called command. Assign to it a new constructor call of put scaling policy command, passing in the params variable. On the next line, just return a call to send auto-scaling command, passing in the command. And that's it to set the policy on our auto-scaling group. So now we have the group being created and the policy being attached. So let's run this file and watch it work. In your command line, execute node create autoscaling.js. After some time processing, it should output the result of the autoscaling group creation. I'm going to skip this video in time a bit, as I usually do, and we can see that the autoscaling group was created successfully, and an instance has also been created for the group. If you go to the load balancers menu option and copy this DNS name into your browser from the load balancer that was created, you'll see the demo project pull up. This is a result of each one of those pieces that we put together over the last few videos. The load balancer is routing our request to an instance that was created by an auto-scaling group using a launch template. Pretty awesome. In the next clip, let's look at limits that you may run into when using auto-scaling and load balancers. Limits for auto-scaling largely define how many of each resource that you can have. The EC2 limits page that we looked at earlier also contains limits for both auto-scaling and load balancing. While these aren't all the limits that exist for auto-scaling and elastic load balancing, they are the ones that you can increase, like the soft limits. But let's take a look at some of the most important limits, in my opinion. With auto-scaling, the main limits are on the number of groups and launch configurations that you can have. I think these are sufficiently large enough that you wouldn't hit them unless you have an entire company working on one account. And again, it's something that you can raise. As far as I can tell, there are no limits on how many launch templates that you can have. So go wild with that. Load balancing limits are also defined around the number of resources. If you do a lot of internal load balancing, the application load balancer limit may not be enough, so just keep an eye on that. Another load balancer related limit is the number of certificates that you can attach to a load balancer, which is set at 1. This is important when you're creating a web application because you'll need individual public internet-facing load balancers for each TLS endpoint that has a unique certificate. You'll actually attach the SSL certificate to a listener, but you can only have one listener on port 443 for each load balancer, so that limits the number of certificates for HTTPS. I've never actually had a problem with this because I've never actually needed more than one SSL certificate on a load balancer, but if you do, that's how you would solve it, by having multiple load balancers. In addition, you can only have one load balancer configured for each target group, but you can have multiple target groups for one load balancer. And that's about it for the major limits for auto-scaling and load balancing. Scaling is the lifeblood of the cloud, and scaling computing resources is one of the most common operations done in AWS. This module walked you through everything you needed to be able to configure scaling efficiently. We started by defining the differences between scalability and elasticity. Essentially, elasticity scales based on configured rules. Then we started implementing our scalable architecture by creating a launch template. Creating the load balancer was next, followed by the all-important auto-scaling group and an auto-scaling policy in addition, the rules that tell an auto-scaling group when to add or remove instances. Finally, we discussed the resource limits you'll work within when using auto-scaling or load balancers. In the next module, we're going to look at different types of storage in AWS, specifically Elastic Block Store for EC2 instances and S3 storage for all-purpose object storage. We'll work from the resources that we created in this module, so don't tear anything down yet. See you next time. Hi there, and welcome back to AWS Developer Designing and Developing. File storage is one of computing's oldest concerns and something every developer has to deal with. There are several different solutions in AWS for storing your files, and each target a specific use case. In this module, we're going to start by discussing options for EC2 instance file storage. Then we'll try our hands at reusing an EBS volume between two EC2 instances. Then we'll switch over to S3 to create an S3 bucket, and then upload objects into that bucket. Finally, we'll talk about some important limits with EBS volumes and S3. Without further ado, let's get to storing. EC2 provides you three different storage options: Elastic Block Store, or EBS, Elastic File System, or EFS, and Instant Store Volumes. Each were introduced at different times, showing a sort of evolution and process for AWS EC2 storage. Instant Store was the first storage type for use with EC2 instances. These volumes are physically connected to the server where your instance is running. They used to be the default storage option, but there are a few reasons why they're not best for general use anymore. EC2 data on an instant store volume is completely wiped if the connected instance stops or terminates. Data stored on an instant store volume is basically stuck. You can't create a snapshot from an instant store volume. You could move the data off the volume, but it's completely up to the user and it's a manual process. EBS is the preferred way to store data with an EC2 instance these days. EBS volumes live independently from the EC2 instance and can be detached for reuse, backed up with snapshots, and allows the instance to be stopped. There are also lots of options in regards to the types of volumes you can connect. This table shows you the options you can choose when creating a new EBS volume. EBS volumes are also replicated within the same availability zone to ensure that there's no loss of data. EFS is an evolution past EBS, but also serves a very specific need. EFS is built to connect to multiple instances at once and scale the file system capacity as needed. The product documentation advertises capacity growing to petabyte scale, but I haven't been able to test that. EFS is good for big data type operations and is more of a dedicated file system which isn't optimized for a root disk for an EC2 instance. EFS provides data durability by replicating volumes across multiple availability zones. In the next clip, we'll play with an EBS volume to see how it can be reused. There are a lot of different things you can do with EBS volumes, like creating snapshots, creating new EBS volumes from snapshots, and attaching multiple volumes to an instance, just to name a few. For this course, I wanted to give you just a taste of some of these EBS operations. In this clip, we're going to detach an EBS volume from one instance and then attach that volume to a different instance. In the scripts 05 directory, we'll start with the stop ec2 instance.js file. This file does more than just stopping an instance. It will first stop an instance, the one that we'll be removing the EBS volume from, but then it will launch a new EC2 instance so that we can attach that volume to that instance. That's going to all happen in this one file. After this, we'll modify a different file that will manipulate the EBS volume, but let's go ahead and modify and run this file first. There are only 3 small pieces we need to change in this file. First, we need to add in the instance ID for the instance that we want to remove the EBS volume from. This will be the instance that we created manually, not one of the auto-scaled ones. Let's go to the EC2 dashboard to find this. Click on the Instances menu option on the left. You should probably have 2 to 3 instances now. One that you created manually, and then 1 or 2 that were auto-scaled. One of them will be the instance that we launched with the AMI from the AWS Marketplace. You can tell by selecting the different instances and looking for the one that has the AMI name of a long string that starts with Bitnami node. When you find it, note which availability zone that it's in. This is going to be important so that we can launch our new instance in the same availability zone. Copy the instance ID and then move to your code editor and paste it as a string for the value of instance ID. Next, in the params object in the create instance function, we have a placement object which describes which availability zone the instance should be launched in. This should be the same availability zone as the instance that we are removing the EBS instance from, the one we just stopped. So enter the availability zone that you remembered from the AWS Management Console. This is all necessary because EBS volumes can only be connected to an instance in the same availability zone that the volume is in. Since the volume was launched in the same availability zone as the instance that was launched previously, we want them to match. This is a practical consideration since the latency when connecting a volume in a different data center in a different availability zone, even though it's super low because it's staying within the AWS network, it could be prohibitive to actually doing anything with CPU. It needs a much closer connection with that storage volume. Now at the top of this params object, we need to add the image ID to use to boot our new instance. The instance doesn't need a special AMI, so just Amazon Linux will do. So go back to the AWS Management Console and you can click this Launch Instance button. Then copy the AMI ID from the very first Amazon Linux 2 entry for the x86 architecture. Then paste that as the value for image ID. Now you can go to your command line and make sure you're in the scripts 05 folder and run node stop ec2 instance.js. This will stop the instance we're going to remove the EBS volume from and create a fresh brand new instance to attach the volume to. This is a great time for a quick note. Why are we actually stopping the instance here? Well, to detach a root volume from an instance, that instance must be stopped. The instance in question only has one attached EBS volume, and that is its root volume. To detach it, we need to stop it first. If it had multiple volumes and we were detaching a non-root volume, well, we could detach that volume while the instance was still running. All right, now open up the reuse EBS volume.js file. This script does 2 things. It detaches a volume from one instance and then attaches it to another. Pretty simple. So let's make this script functional. The first step is to find some IDs. We will need the volume ID of the EBS volume that we'll be detaching and the instance ID of the EC2 instance that we just created. For the second value, you can get that from the command line. In the output to the command we just executed, copy the instance ID and paste it as a string for the value of instance ID. For the volume ID variable, we need to go to the EC2 dashboard again. In the left-hand side menu, click on Volumes. You should have a number of volumes here equal to the number of running instances. Which volume ID do we want? Well, we need the volume attached to the instance that was stopped. So look at the instance ID that you had copied and select the volume that is attached to that instance. Then copy the volume ID and paste it as the value for volume ID. Now with the correct values in place, let's implement the detach volume function. Start by declaring a params const object. The only property that AWS needs to know when detaching a volume is the volume ID. So add a volume ID parameter and set the value to the volume ID argument that we passed in. Then on the line after the params object, add a new command const variable. And then assign to it a new constructor call of detach volume command, passing in the params variable. Then on the line after that, you can add the return keyword and then call send command, passing in command. Now, once the volume is detached, it'll be available to be reattached to another instance. So let's implement attach volume now. First, create a params const object. The first property to add is instance ID, which designates the instance to attach to. Set the value to the instance ID function argument. The second property is volume ID, which is the volume to attach. Set the value to volume ID. And then the last property we'll add is device. This defines the name that will be used to mount the volume on your instance. These values are usually things like /dev/sda1 or dev/xvda. These are all kind of like Linux mounting things. We'll call ours something way more creative than those. Enter /dev/sdf. All right, so now on the line after the params object, create a new const called command. Assign to it a new constructor call of attach volume command, passing in the params variable. Then after that, add the return keyword and call send command, passing in the command. Now, when we run this, it'll swap the volume in question to the new instance. There's just one more thing to do though. We need to stop the newly created instance before we can attach this EBS volume to it. More stopping? Why do we need to do that? Well, any volume launched from an AMI with a thing called a product code cannot be attached to a running instance. I believe this restriction is in place because when an instance starts up, any product codes on attached volumes are copied to the instance and then they're used to make sure the correct subscriptions and charges are applied to that running instance. So it's sort of a compliance billing kind of concern. Unfortunately, AWS has pretty much hidden any possible way to find out if a volume has a product code anymore. They've removed it from the management console. There's no CLI operation that'll show it to you. For volumes that you've launched from a custom AMI that you own in your account, you can view the product code that is still shown on the snapshot for that AMI. But otherwise, you just have to try to attach it and see if you get an error. I know we'll get an error, so we're just going to go ahead and do this. But regardless, it's probably actually a better idea to stop an instance before attaching a volume if it's possible. So let's go shut down the instance. Move to the EC2 dashboard in the AWS Management Console. Click on the Instances menu option and find the instance we just created. You can tell by the AMI ID that's shown on the instance. It should say Amazon Linux too. Select it and then click the Instance State dropdown and then Stop Instance. Yes, we could have done this with our file as well, but this is just a little bit quicker. I'm sure you don't want to write any more code that is unnecessary. You will need to keep an eye on this instance to see when it has finished stopping. But I'm going to skip in time a little bit here so you don't have to wait with me. In your command line, run the command node reuse ebs volume.js. Once you get some output, it should have detached and reattached the volume to the new instance. Now we can check our work by going to the EC2 instances in the AWS Management Console. refresh it, and select the target instance that was attached to. In the instance details, click on the Storage tab, and there's a section for block devices, and you should see the volume that we just attached. It should have the device name dev/sdf. Now, you could start the instance again if you wanted to, because it's currently stopped. And if you did that, you'd then have full access to all the data that's on that volume. There's plenty more that you can do with EBS, but I hope that this gave you just an idea of the versatility of the service. In the next clip, we're going to get started with S3 buckets. S3 is a monster in AWS, often rivaling EC2 in its ubiquity across the cloud provider. The reasons for its popularity are the reliability, speed, and ease of use that it has. But there are some automated aspects of the service that make it even more useful for applications. Two of those features are versioning and lifecycle events. Versioning allows you to store multiple iterations of the same object in case you need to access a previous revision. This can be configured at the bucket level and applies to creating, deleting, or modifying. When a file is created, it becomes the current and only version of that file. If you upload a new file with that same key, the new upload becomes the current version and the original is retained with a unique version ID. If you then delete the file, it shows as deleted, but you can always get the older versions of that file. As a simple bit that can be flipped on a bucket, versioning is tremendously useful. The only downside is the cost of keeping multiple versions for each file. Each version of a file is charged the exact same as the file itself. So depending on how often a file is replaced or deleted, this can multiply your S3 costs quite a bit. One way of managing those S3 costs, not only for versioning but also for normal usage, is by configuring lifecycle events for your bucket. A lifecycle event allows you to set certain rules for what to do with an object in your bucket once a certain number of days has passed. One lifecycle event you can trigger is to move an object to a lower cost type of storage. For instance, you can say that once a file has been in S3 for 5 days, move it to either S3 infrequent access storage or Glacier storage. Both offer much cheaper costs for files that don't need to be accessible quickly. You can use this option for previous versions of files as well. This means you can move them to Glacier and offset the cost of having versioning on your S3 buckets. The other convenient lifecycle event is expiration, which allows you to delete files once they've existed for a given number of days. As with moving objects, you can apply rules to only affect previous versions, permanently cleaning out older versions once they've been retained for a certain amount of time. Using both of these features can add to the robustness and usefulness of S3 as the ultimate storage utility. In the next clip, let's get started by creating our first S3 bucket. The most fundamental construct in S3 is the bucket, and it's required before you actually store anything in the service. So let's create a bucket so that we can store the assets for our demo project. In the scripts 05 folder, open the create s3bucket.js file. This script is super simple. It just creates an S3 bucket with a name and some configured permissions. That's it. We'll start by creating the name for our bucket. Now, S3 bucket names do have to be globally unique, which means that you'll need to add something to the end of this bucket name to make yours different from mine and everyone else's. So replace the comment after hamster/bucket with, I don't know, whatever you want. Also, make sure your bucket name does not contain an underscore. So maybe not whatever you want, just whatever you want as long as it's not an underscore. We will be using the bucket name in a domain name later, and underscores aren't allowed in URLs for some reason. Now let's implement the create bucket function. Start by creating a trusty old params const object. Creating this bucket doesn't require a lot of properties. The first property is bucket, and you can give it the value of the bucket name function argument. The next property is ACL, all uppercase, and it stands for access control list. This basically defines the permissions of the bucket and its objects. The value here is one of the several canned ACLs that AWS provides. which are just predefined sets of permissions. Enter the string public-read as the value here. And with our params object complete, we can now create the bucket. On the next line, create a new const command and assign to it a new constructor call of createBucketCommand, passing in the params variable. Then add the keyword return on the next line and call send s3 command, passing in the command variable. This is a command sending function that has been imported from the helpers file up above that I wrote previously. It uses an S3 client to send the command. And with that, our script is done. You can go ahead and switch over to your command line and execute the command node create s3 bucket.js. You'll see some output once it's complete and your bucket will be created. If you really want to, you can double check in the management console as well if you want to ensure that the bucket creation was successful. In the next clip, we're going to upload some of our demo project static assets to this bucket. S3 buckets are great for storing all types of objects, pictures, videos, text files, you name it. It's particularly nice for static assets for websites, and that's what we'll be using it for. We'll be using the file upload s3objects.js, so open that in your code editor. Just like with other files, I've already written a lot of code to help you out here, specifically the code that's going to be loading files from your file system to upload. The modifications to this script will only target the put object to S3 operation. So start by replacing the string value in the bucket name variable with whatever you set it to in the last video. The execute function is where the code actually runs. A helper function is called that gets all the files in the public folder of the demo project. Each one of those files is iterated through with a for loop. The upload s3 object function is called on each file, and then the e-tag confirmation is logged to the console. That's it. So let's implement the upload s3 object function. Start by declaring the params const object. The first property is bucket, which you can set to the bucket name function argument. Obviously, this is where we want to upload the file to. The next property is ACL, which is pretty much the same thing as the property that we used when we created the bucket. But this ACL property is specific to the file that's being uploaded. And since all the files should be exposed to end users, enter the string public-read here. The next property is body, and this is the actual file contents, which can be accessed by setting the value of the property to file.contents. The next property is key, which is the object key identifier that should be used in S3. We can use the file name for that, so set the value to file.name. The next property will be different for each file, and the property name is content type. This should match whatever type of file is being accessed. So I've created a helper function called helpers.getContentType. Call that here and as the value, and then pass in file.name. The helper function will return the correct content type based on the file extension from that file name. And that's it for our params object. On the next line, create a new const called command. Assign to it a new constructor call of putObjectCommand, passing in the params variable. After that, enter the return keyword and call helpers.sendS3 command, passing in the command variable. And that completes our modifications for this file. Move over to your command line. We do need to build the project once so that the JavaScript and CSS files are generated. We haven't done that yet for this demo project. Run the command npm run build. This will run Webpack to compile all the assets, and it can take a while. It doesn't have any output. It's just going to sit here on this blank screen, but once it's complete, it'll send you back to the prompt. Then we can upload the files. Execute the command node upload s3 objects.js. This operation may take a little longer depending on your upload speed from your computer, but once it's complete, you'll see the output for each file that was uploaded. Our files are now in S3, yay! But we aren't using them yet. Oh, we need to update our asset references in the demo project source code. So switch over to the AWS Management Console and go to the S3 dashboard. Click into the bucket that we created and select just any one of the files here. Just click on the file name. I'm going to use application.min.js. This object URL value is what we want, but we really only need part of the URL for our purposes, which is everything in the link up until the file name. So select and copy that, and then we'll use that with the asset references in our demo project. So move over to your code editor. We only have two places in our application where we need to modify the path for the assets. And the first is in the handlers/template directory. The file is index.html. On line 5, we're importing a style sheet. And right now it's referencing that style sheet from the public directory. So remove the public part of that path and paste in what you got from the S3 object. Make sure there's not a double slash there before style sheet. Your path should look something like this. The main difference is going to be your bucket name. On line 7, do the same thing with the reference to the favicon icon. Then on line 12, we're bringing in the JavaScript file. So again, remove public and paste over that path. The other place that we need to modify the path is in the util folder. And the file is assets.js. At the very top of the file, there is a base const being created, and it should have public right now. You can remove that completely and paste the S3 URL that you have. Just make sure that there is not a slash at the end so that the final path for those images is created correctly. In the next clip, we're going to look at some limits that you may run into with EBS and S3. Both EBS and S3 have limits that you might actually hit a little bit more than some of the other services that you've seen. With EBS, I've already mentioned the limits around attaching and detaching, but I'll reiterate them here. An instance must be stopped in order to detach a root volume. If the volume isn't a root volume, then it can be detached at any time without the instance having to be stopped. An EBS volume can be attached to a running instance at any time as long as it does not have an AWS Marketplace product code. If that exists, then the attaching instance must be stopped. One important limit about EBS is that volumes can only be attached to instances that are in the same availability zone. While EBS snapshots are stored across availability zones, instances and volumes must be in the same availability zone to keep latency low. With S3, there's a soft limit on the number of buckets allowed, and it's set to 100 at default. Within a bucket, there's no limit to the number of objects aside from the size of your wallet. As mentioned before, bucket names must be globally unique, not just unique in your account. And that's most of the limits you may hit in your daily usage with either service. There's no limit to the number of uses for file storage, and we were only able to cover a small amount here. Regardless, this module has given you a good overview of EBS and S3, and hopefully sparked your imagination for what you might want to use them for. We started by talking about the trade-offs between file system types for EC2 instances with EBS, EFS, and Instance Store. Ultimately, EBS was the best for our purposes. Then we went through the practice of detaching and then reattaching an EBS volume between two different instances. Next, we got into S3 storage and created our first bucket. But an empty bucket is worse than useless. So then we uploaded all of our static assets from the demo project to the bucket. Finally, we talked through some common limits found in EBS and S3. In the next module, we're going to look at another type of persistence in AWS as we look into DynamoDB and RDS and using Redis caches with Elasticache. Make sure you stick around and I'll see you in the next module. Hello there, and welcome back to AWS Developer Designing and Developing. Along with computing and storage, databases and persistence are the third pillar upon which stands the halls of AWS. There are plenty of different persistent solutions in AWS, and they continue to upgrade and add new ones every year. The key solutions are DynamoDB for NoSQL and quick document data storage, RDS for traditional relational databases, and Elasticache for short-term caching. In this module, we're going to start by looking at how provision throughput and secondary indexes work in DynamoDB. Then we'll create a DynamoDB table to store our hamsters and look at a few ways to query and get data out of that table. Next, we'll learn how to create an RDS database with the SDK and connect our code to that service. Then we'll work with Elasticache with the SDK by creating a cluster and then using that to cache our user sessions. And finally, we'll look at the all-important limits we may hit when using DynamoDB, RDS, or Elasticache. Throughput capacity in DynamoDB is the key measure for how your tables will perform. There aren't really any other attributes in the table that you need to configure, but throughput isn't exactly that simple. At its most basic, it can be defined as the number of records you're allowed to read or write per second, up to 4 kilobytes for reading and 1 kilobyte for writing. But there are so many caveats and details to that description that it sometimes needs a full video to explain, which is why we're here. I want to start by going over how to calculate throughput and then go over each type of capacity mode for DynamoDB tables. AWS has released many new innovations with these over the past few years, so there may be some surprises here for you. So let's talk through some scenarios to better understand how this provisioned throughput thing works. We'll start with a simple table of hamsters, like the one we'll set up later in this module. We'll configure this table with 5 units of provisioned throughput for reading and writing. Now let's say we have 6 hamster records locally that we're going to populate the table with. If we do a batch write call, it'll essentially try and write all 6 records at once. There are a couple of considerations here. How large are the records? In our case, they are only a few properties with not much text and come in at under 100 bytes each. Dynamo will round up each write to 1 kilobyte if it's under, so each write will consume 1 unit of provisioned throughput. But wait, that means we'll be writing 6 units at once, which exceeds our 5 provisioned units for writing. Well, in this case, you will have one of 2 things happen, and you won't be able to really guarantee which will happen. Either the 6th write will return a provisioned throughput exceeded exception, or burst capacity will be consumed and the write will go through. AWS documentation says that burst capacity will be used when it can, but there's no guarantee. This basically means if you occasionally exceed your provisioned throughput, AWS may let the requests go through. Because we're using the SDK, it actually already has built-in code that retries if it gets a provisioned throughput exceeded exception. So you'll likely rarely see that error unless it's an extreme case. Now let's look at reading the records once they've been populated. Let's say you want to get all 6 records at once, doing a scan. There will be 6 reads that will happen within a second. And even though the records are well below the 4 kilobytes reserved for each unit, each will consume a full unit. It'll round up. Except they won't, because by default, the SDK does an eventually consistent read. If you're doing eventually consistent reads, you get double the reads per unit. So each unit will give you 2 reads instead of 1 read, which if you were doing a strongly consistent read, you would only get 1 read out of that unit. The consistency here relates to AWS replicating your data across availability zones in a region. Eventual consistency will get you the record, but it may not have very recent changes to it. Strong consistency ensures that you get the newest version of a record with any changes, no matter how recent. So back to our hamsters. Our scan of 6 items with eventual consistency will actually only consume 3 read units, which is quite convenient. Now we'll just run through another quick example. Let's assume we've got a table with some binary items. They're about 20 kilobytes each. How many units would it consume to read one item? Well, if we're doing eventually consistent reads, it would take 3 read units. Each unit in this consistency will hold up to 8 kilobytes. A 20 kilobyte item will technically use 2.5 units, but AWS rounds up, so we've got 3. What about if we wanted to read it with strong consistency? Now it would take exactly 5 because each unit would only account for 4 kilobytes. Let's look at writing then. How many write units would it consume? Unfortunately, there's no consistency discount for writing, so a 20 kilobyte item would consume 20 write units. That's a lot more than reading for sure. Now let's talk about the capacity modes in DynamoDB. There are 2 modes: provision capacity, which is the original mode, and on-demand mode, the new mode that is more flexible. Let's look at provision capacity mode first. With provision capacity, you specify the number of reads and writes per second for the table or index. Any requests above those limits could be handled by burst capacity or could be rejected. AWS has released auto-scaling for provision capacity mode, so you could configure rules that would scale the provision capacity up or down based on an increase in requests. With the configured reads and writes for your table, you do pay regardless of whether you actually are using that capacity or not. And then there's on-demand capacity mode. This was released in the last couple of years and is a model that charges you per read and write requests. Unlike provision capacity, you don't pay for anything that you don't use. However, the read-write requests do cost more than if they were configured with provision capacity. You gain flexibility, but it may be more expensive depending on actual use. On-demand capacity also scales as needed. You don't need to configure anything. It's a true set it and forget it capacity mode. And that's about it. Hopefully those examples have given you an idea of how throughput is calculated in AWS. And the capacity mode review has given you some ideas for configuring your tables. In the next clip, we're going to talk about Dynamo keys and indexes. In order for DynamoDB to achieve high performance, it spreads your data across many different partitions. The attribute it uses on each item to decide which partition to use is called the partition key. Also, sometimes it's called the hash attribute. This key is passed to an internal hash function, and the output is used to assign the item to a partition. This partition key must be unique in your table, kind of like a traditional primary key. There's another type of key schema you can use instead that lets your partition key be non-unique, and that's by adding a sort key, also sometimes called a range attribute. In the case that you define both of those keys, Dynamo will use the partition key as input to the hash function to find which partition to use, and then it'll use the sort key to sort all the items found at that partition location. Both of these key schema types allow you to be very flexible when defining how your table should work. But sometimes a single set of keys isn't enough to properly query your data. In this case, you can use a secondary index to provide alternate query methods. There are 2 types of secondary indexes: global secondary indexes and local secondary indexes. Let's start by discussing global secondary indexes. With a global secondary index, you define a new key schema to organize your items and query on. You could have a partition key schema or partition key plus sort key schema. In addition, you'll define which attribute you want to include in the index. If you query on the index, only selected attributes will be accessible. In some ways, Dynamo is just replicating the data and organizing it in a different way. Another nice thing is that when you create a global secondary index, you define new provision throughput capacity exclusively for the index. When querying on that secondary index, only the throughput configured for that secondary index is used. A local secondary index is very different from a global one. With a local secondary index, you define an additional sort key to query data at the partition level differently. The original table's partition key is used in conjunction with the local secondary index's sort key to query the data. Additionally, you don't create provision throughput capacity or define a set of attributes. all of the base table's properties are carried over. In many ways, a local secondary index just enhances the original data, where a global one creates an exclusive new set. And with both indexes, Dynamo maintains them completely when adding or deleting items, updating the indexes, and you don't have to do anything. In the next clip, we're going to put some of this information into practice as we create a DynamoDB table. The first step we need to accomplish is to create a table in DynamoDB that we can use to store data. In our case, we'll be creating two tables to store the data for hamsters and races. In the scripts 06 folder, open the create dynamo table.js file. You can see in the execute function, we'll be using the same create table function twice to create a hamsters table and a races table in DynamoDB. Both tables will use the same key schema, which is how we're able to do both operations so simply like this. So let's go ahead and implement the create table function. Start by creating a params const object. The properties needed to create a Dynamo table will take into consideration the schema and keys of the table, as well as the performance attributes of that table. We'll start with the first property called table name and give it the value of the table name function argument. A quick note here, table names do need to be unique in each region at the account level. If you use different regions, you can reuse a table name. The next property is attribute definitions with the value of an array. These attribute definitions aren't used to define the whole table schema or anything. They really only define the attributes we'll be using as our key. Inside the array, create an object. The first property here is attribute name, which will give the value of a string with the value ID. The next property is attribute type. Here we've got three options: S for string, N for number, or B for binary. In our case, our IDs will be numbers, so enter a string with the value of an uppercase N here. That's the only attribute we need to define. After attribute definitions, add the property key schema. This will also be given the value of an array. Here is where we define our table keys based on the attributes we defined. Inside the array, add an object. The first property here will be attribute name, which will be the string ID. This needs to match the attribute name defined in our attribute definitions. The next property is key type, which we'll enter as hash in all uppercase. Now, after the key schema property, we'll add the last property, provisioned throughput, which is an object. Add the property read capacity units with the value of 5. Then the property write capacity units, also with the value 5. And those are all the properties needed to create our table. Now on the next line, create a new const called command, and then assign to it a new constructor call of create table command, passing in params. On the line after that, you can add the return keyword and then call send dynamodb command, passing in command. Now our script is complete, so switch over to your command line and make sure you're in the scripts 06 directory. Then execute the command node create dynamotable.js. When it's complete, you should get some output on the second table that was created. We just threw away the output from the first table creation. The tables will take a few minutes to be created, but then we'll be able to use them. In the next clip, we're going to populate those tables with some data that our demo project needs to use. An empty Dynamo table is worse than an empty S3 bucket. Okay, maybe not, but still we want to populate our Dynamo table with some data. In your scripts folder, open the file populate dynamotable.js. Let's go over what's happening in this script. I've created some helper functions to get the initial hamster and race data. Then, after it's retrieved the data, it will populate the respective table with it. That's pretty much it. I want to bring another thing to your attention. If you look at the command import at the top of the file, you will notice that it is not importing from client DynamoDB, but instead from lib DynamoDB. This is a higher level library than the bare bones client, the client DynamoDB. It makes working with DynamoDB items way easier by handling the serializing and deserializing of DynamoDB data types. If you've used the DynamoDB document client from version 2 of the AWS SDK, then you already know what this library will do because it's functionally the same code. When we send this command, we will use a DynamoDB document client instead of the regular client to send the command. Now let's implement the populate table function. The input to populate the table will be dynamically created from the data function argument, and then we'll use the batch write command to write all the items at once. So we'll start by declaring our params const object. This one's a little weird because it has a single root property, request items. Give that property an empty object for the value. Then inside, our property key will be the name of the table that we are inserting to. To get this from the table name argument, use square brackets and put the table name argument inside. We'll build the value for this dynamically, so give it the value of a call to data.map and pass in an arrow function with one argument called I. Inside, we'll return an object with the property put request. As a note, you can include other types of requests in this object, such as delete request, and the batch write function processes both, which is pretty convenient. Now for the value, create another object and give it the property item with the value of the I argument. Again, because we're using the DynamoDB document client, it'll take care of converting the item to a DynamoDB compatible object. And with this, the items for the put request will be built out dynamically, one item at a time. On the next line, create a new const called command. Assign to it a new constructor call of batch write command, passing in the params variable. Then on the line after that, add the return keyword and call send dynamo item command, passing in command. And that's it for this script. So let's go ahead and try it out in our command line. The tables that we created in the last video should be finished creating by now, so go ahead and run the command node populate dynamo table.js. When it's done processing, move over to the AWS Management Console and go to the DynamoDB dashboard. Click on the Items menu option on the left, and then select either one of the tables. You should see the items which we pushed, so everything is complete. In the next clip, we're going to connect our demo project up to this table to consume the data that we just put there. In this clip, we're going to look at two of the main ways to get data out of a DynamoDB table. The easiest way to get data out of a table is to just use the primary key of the item that you want to get. By utilizing this method combined with secondary indexes, Dynamo becomes a very flexible and powerful tool. However, there are some other methods for retrieving data that we'll look at in this clip, and those are scanning and querying. We'll get a chance to use both as we get the hamster and race data that we need. For this, we'll be modifying several files in our demo application. To start with, go into the lib folder, then data, and then lib again. Very creative with my directory names. We'll be modifying the dynamo.js file here. This file abstracts some common Dynamo operations that are called often. The functions can be used with any table and query. You'll see with the imports that we are using things from both the DynamoDB client and the library. We're importing the regular DynamoDB client and then the DynamoDB document client and some commands. This send command function is like the one I previously hid in a helpers file. You can see a barebones client is created, then that is used to create a document client. We're using this document client because we'll be working with Dynamo items, and the document client greatly simplifies these operations. Let's start by implementing the getAll function. This function will use one of the first Dynamo data retrieval methods, scanning. A scan will take a table and an optional start key and attempt to get all the items from that table. Scans return 1 megabyte chunks of data. This means if your table has more items than that, you'll need to do multiple scans to get all the data. A single scan will only return the number of items that can fit into that 1 megabyte, and then it'll return a start key to use with your next scan. For our purposes, we will only have to perform one scan since our data set is small. Start by creating a params const object. For the scan, we only need one property, table name. Give it the value of the table name function argument. Then in the next line, create a new const called command. Assign to it a new constructor call of scan command, passing in the params. Then after that, create a new const called response. We need to modify the result from the scan to only return the items from that result. After an equal sign, add the await keyword and call send command, passing in command. Then in the next line, add the return keyword and then response.items with an uppercase I. This is how we can access the items from the response, and the document client will make those items native JavaScript objects. And that's all our getAll function needs, just this simple scan command. The get function will be a little more complicated. You can see by the function signature that we're passing in the table name and an ID. It's true, with these arguments, we could just do a call to get and immediately receive the relevant item. But this is also a great place to use query instead. So let's do that and query by the ID. Start by declaring a params const object. Add the table name property first and give it the value of the table name function argument. The next property actually defines the query we're using. Create a property called key condition expression. The value will be a query on the key, so enter a string with the value ID equals :h key. This query will find any records where the ID of the record equals whatever we set as h key. The colon before h key indicates that it is a variable. We'll add the variable with the next property, expression attribute values. This will have the value of an object and the property will be :h key in quotes. The value will be ID, but add a plus in front of it so that it will be coerced into a number in case it's passed as a string. And with this, the ID argument is added to the params and configured correctly to work with the key query. On the line after the params object, create a new const called command and assign to it a new constructor call of query command, passing in the params variable. Just like getAll, we need to modify the command response before we return it. So on the next line, create a new const called response. After an equal sign, add await and then call send command, passing in the command. Then on the next line, add return and then response.items. When you use a query, response is an array. For this get function, we just want to return one item, which would be the first item in the array. So then reference the first item with bracket notation and the index of 0. Great, our Dynamo functions are complete. So let's use them. Move up one directory and open up hamsters.js. We want to change the sources of our hamsters and races data from the current mock to the Dynamo file that we just modified. On line 2, we'll change the value of the data source import by removing the right-hand side of the assignment and replacing it with a require function call, passing in the string ./lib/dynamo. Now save that file and open up races.js and make that same change to line 1 to import that Dynamo file that we edited. And that's it for our Dynamo changes. In the next clip, we are going to move back to relational SQL land. If Dynamo doesn't work for your needs, you can always use a trusty relational database. The relational database service in AWS is great because it takes care of the maintenance tasks that all databases need performed, including automated replicas and backups. The data we're working with in the demo project is simple, so it could really live in either Dynamo or RDS, but I split it up so that you can have an example of working with each. In the scripts 06 folder, open the create rdsdb.js file. In this file, we're going to do exactly as it suggests and create an RDS database. We'll use it to store the user and user favorites data from the demo app. All the modifications for this script are in the create database function, so let's implement that. Start by creating a params const object for our database creation properties. The first property will be allocated storage, which lets us configure the storage size of the database. The number is in gigabytes, and there are some upper and lower limits depending on the database engine. We can enter 5 here to represent 5 gigabytes, since that is the minimum size allowed for a MySQL instance in RDS. The next property will be DB instance class. It's kind of funny because they alternate between calling this value an instance class or an instance type, but ultimately it's just the same as an instance type, like with EC2. We can use the smallest instance type available here, db.t2.micro. The next property is DB instance identifier. You can set the value to the DB name argument. Then we have the property engine, which is the database engine that you want to use. You know, I really wanted to use AWS's own Aurora database engine for this course, but it's not eligible for the free tier, and it can only be created in clusters, not individual instances. So it's a little more complicated. Instead, let's just set this to the string MySQL. Next, add a property named dbName and give it the value dbName. The next property is VPC security group IDs. There are actually 2 types of security groups applicable to an RDS instance: DB security groups and VPC security groups. VPC security groups are more versatile, which is why we're going to be using them here. DB security groups are old, and they're actually only applicable when you have an EC2 classic configuration, which you probably don't, and you probably don't want to figure out how to set one of those up. It's kind of an old way of doing things. For the value of this property, create an array and add one item, the SGID argument. The last 2 properties are the database credentials. Add the property master username and set it to the string admin. Then add the property master user password and set it to the string my password, all lowercase. We are setting them explicitly here because that's what's already written in our code. Now in the next line, create a new const called command, and then assign to it a new constructor call of createDBInstanceCommand, passing in the params variable. Then in the next line, return a call to send RDS command, passing in the command. And that's it for this function. Let's run this file to create our database instance. Switch over to your command line and execute the command node create rdsdb.js. When it's complete, it should spit out the details of the instance that was just created. Getting an RDS instance booted up can actually take some time, but we do need to modify some code in our demo application to utilize this database, so let's just do that. Back in your code editor, open the file lib/data/users.js. Instead of writing queries to the database manually, the demo app uses the Sequelize ORM library to do all the database interaction. It provides an abstraction that lets you treat querying the database like you're accessing functions. On lines 1 and 2, we import the user and user favorites objects from Sequelize. These are currently pointed to a mock, so let's update the reference. For user, change it to require, and then in the parentheses, do ./lib/models/user. And then for user favorites, change it to require, and then ./lib/models/user favorites. The next change is to modify the actual connection to the database. So open the file lib/data/lib/mysql.client.js. The only change necessary here is to change the value of host to the actual host name of the RDS database. To get this value, let's head over to the AWS Management Console and the RDS dashboard. On the left-hand menu, select Databases and then select the database instance we just created. Now, because it takes a while, it's possible that this instance will still be in the process of creating. But as usual, I've skipped my video in time a few minutes here, and you can see that it's already finished. You may have to pause the video and come back. When it's finished creating, scroll down to the endpoint value and copy it. Now back in your code editor, paste this value inside the string next to host. And that's it for the changes required for creating and using an RDS database. In the next clip, we're going to configure a Redis cluster in Elasticache. Elasticache provides managed caching services that are particularly useful to web applications. There are two open source cache engines, Redis and Memcached, that can be used with Elasticache, but over time it really seems that Redis has come out as the clear, better solution here. We're going to create a Redis cache cluster and then use it to cache the user sessions in the demo app, ensuring that our application can scale to a whole lot of users without impacting application performance. In the scripts 06 folder, open the create redis cluster.js file. The only function we need to implement here is the create redis cluster function. The only arguments it takes is the name for the cluster and an ID of a security group for the cluster. We'll start by creating a params const object. The first property is cache cluster ID, which is basically the unique identifier for the cluster. We'll use the cluster name argument as the value here. For the next property, add cache node type. This is like the EC2 instance type. We'll use the smallest available for our purposes. Add the string cache.t2.micro. Next, add the property engine and give it the value of Redis as a string. This just tells Elasticache what type of cache that we want to create. The next property is num cache nodes, which says how many nodes or instances that you want to give the cluster. For Redis, the value must be 1, so just enter that here. Then add the property security group IDs and set the value to an array with one item named sgid. In the next line, create a new const called command. Assign to it a new constructor call of create cache cluster command, passing in the params. In the next line, use the return keyword and call send Elasticache command, passing in the command. Now we finish the script, so we can run it by switching to your command line and then executing the command node create redis cluster.js. Once it's complete, your Redis cluster will be booting up. And just like RDS, this can take some time. Once it's finished, we'll need to get the host of the Redis cache to be able to add things to our code. But there's some things that we can go ahead and do. I've already written most of the code to use the Redis cache in the application, so really you just need to make a few minor changes. In index.js at the root of the project, there are a couple of sections that we need to uncomment. This section at the top inside of options is the first, so uncomment all of that. This will configure our happy web server to use a Redis plugin and make a connection to it to use as a cache. Then scroll down to where we define this cache const and uncomment the line with the property cache. This will set the Redis cache as a default cache to use for user sessions. Before it was just using memory. Now go back to that top section of code that we uncommented, and here we need to add the host of the Redis cache cluster that we created. So because the cache creation can take a while, I'm going to skip my video ahead a few minutes here, and the cache is now available. So in your AWS Management Console, go to the Elasticache dashboard and click on the Redis menu on the left-hand side menu. Expand the cluster that we created and copy the primary endpoint field, excluding the colon and the port at the end. Now back in your code editor, paste the value inside the quotes for that host property in the options object. Now you can save that file and the demo app is all ready to use. Now it would be really great to be able to just try out all of this stuff locally. In fact, the DynamoDB and RDS stuff can be run locally, but unfortunately, we can't easily access a Redis cluster running in Elasticache outside of the VPC. We could configure a jump box or a bastion host to access it, but it's just a little overkill for this course. Instead, we're just going to update the code, deploy what we've got locally to our instance in AWS, and see it work remotely. In your command line, navigate to the root of the project. I've created a deploy script that will push your code out to your instance and get it running. All you need to provide is an IP. So go to the EC2 dashboard and the auto scaling group screen. Select our auto scaling group and then the instances tab. You should see just one instance, so select it. Now grab the public IP. We're going to use this in our command line, so switch back to it. Run the command npm run deploy -- and then the IP. If you've followed the video exactly up to this point, you should be able to just run this command and not have any problems. If you made any modifications, you may need to update some of the values in deploy.js. Now, on running this command, it will zip up all your code, upload it to the instance, extract the zip file, install the dependencies, terminate any node applications that are running, and then restart the application. You should be able to try it out then in your browser using the load balancer DNS name. In the next clip, we're going to look at limits you may run into when working with any of these persistent services. As you might expect, DynamoDB, RDS, and Elasticache have some more significant limits than the other services. Persistence is a much more touchy subject and requires both heightened security and a more strict environment in order to achieve high performance. Let's take a look at some of the limits and restrictions. Dynamo has several restrictions around secondary indexes. You can only create up to 5 global secondary indexes and 5 local secondary indexes per table. Those local secondary indexes must be created at the same time as the table and cannot be deleted after. Global secondary indexes don't have this restriction. Finally, when creating a table, tables with secondary indexes must be created consecutively. More than one cannot be created at the same time. RDS has limits around numbers of databases and size of the databases, which is in the terabytes, but nothing you wouldn't expect. There are some restrictions about database and user naming, but they differ with each database engine, so you'd need to research those yourself. Elasticache, similar to RDS, has a limit around the number of clusters and nodes. These are soft limits and can be raised with a request to AWS. The one restriction to remember is that you can't directly access Elasticache from outside of the VPC it's created in. Beyond that, there's no other restrictions that need mentioning. With so many different options for persistence in AWS, hopefully this module has been enlightening and will help you to make the best choice for your use case. Let's recap what we covered in this module. We started out by going over some fundamental DynamoDB topics around provision, throughput, and secondary indexes. Then we created a DynamoDB table with the SDK and populated it with hamsters and races. Next, we learned how to retrieve data from the table with queries and scans. Then we moved on to RDS and created a MySQL database for our user-related data. Next, we created a Redis cluster in Elasticache and used it for our user session state. And finally, we took a look at the limits and restrictions around each of these services. In the next module, we're going to look at how to configure different types of external routing using AWS services like Route53 and API Gateway. Hi there, and welcome back to AWS Developer Designing and Developing. We've been doing all sorts of cool things with AWS in this course, but what good would any of it be if users couldn't access our hard work? That's where Route53 and API Gateway come in. Both provide external internet access to your internal AWS resources. Route53 is direct DNS routing, whereas API Gateway provides an abstraction over routing and is based around REST API design. We'll use both to route our demo project in different ways, so let's look at some of the topics we'll cover in this module. We'll start by discussing the types of routing policies available in Route53. Then we'll see how to configure a hosted zone and record set in Route53 to support a domain name. Next, I'll explain what API Gateway is and how it works. Then we'll go about creating, configuring, and deploying an API Gateway. Finally, we'll end the module by discussing some of the many limits with Route53 and API Gateway. Let's get started. While Route53 is often used as simple DNS rules to route to AWS resources, There's more advanced functionality available in regards to how the routing takes place. Routing policies allow you to define the behavior a routing rule follows once a request has come in. There are 5 types of routing policies that we'll discuss here: simple, weighted, latency, geolocation, and failover. A simple routing policy is when you want to map a single DNS record to a single AWS resource. For instance, sending the domain name hbfl.online to a single load balancer. A weighted routing policy lets you configure multiple resources for a single DNS record and gives each of the resources a weight. Route53 will route requests to each resource based on its percentage of the total weight. For instance, if you configured 2 resources with a weighted routing policy, one with a weight of 1 and the other with a weight of 2, it would route requests to the first resource a third of the time and route requests to the other resource the other 2/3 of the time. A latency routing policy is really useful to reduce the latency for your users with your application. It allows you to configure multiple resources and define regions for each. You'll configure the region in the record set to match the region of the resource. Then when a user requests a domain, Route53 will determine which request will have the lowest latency based on the available regions that you configured and the IP of the request. This is done automatically, so it's a pretty convenient way of dramatically reducing latency. A geolocation routing policy is similar to latency routing policies. Where latency automatically routes based on lowest latency, geolocation lets you configure which requests will go to which resources based on continent, country, or subdivision, which is a state or a province. This gives you tremendous control over who goes to what resource and is likely very useful for legal or compliance reasons. Finally, there's failover. A failover routing policy allows you to configure 2 resources, one as primary and the other as secondary. If the health of the primary resource fails, then requests will be routed to the secondary resource. This provides some stability for domain records when a load balancer won't work. Between all of these routing policies, you should be able to find one for whatever need you have. In the next clip, we're going to configure Route53 for a domain name. Route53 has 2 key concepts to know when setting it up to support a domain name. The first is the hosted zone. This is basically the domain name itself without subdomains. For instance, example.com or hbfl.online. The other concept is the record set. This is basically a DNS rule which configures an AWS resource as the destination of a request. Each hosted zone will have many record sets in it. In our case, we're going to create a hosted zone for our demo project and then configure a route set to send requests to our load balancer. One note before we start: unless you purchase a domain name from a registrar and add the name servers from your hosted zone, you won't be able to actually test the changes we'll do in this video. So if you do want to follow and test it, purchase a domain name and use that instead of the placeholder here. Now switch over to your code editor and open the file in the scripts 07 directory named createroute53hostedzone.js. This file is simple, with just one method that we need to implement. For this script, we'll be using the Route53 client, and as usual, I've already implemented the send command method in the helpers file. Let's implement the createHostedZone method. Start by declaring a const named params. There are only 2 properties that will be needed. The first is the name property, which you can give the value of the hzname argument. Above, we're passing this in as hbfl.online. If you wanted to use your own domain name, just update the string for the hzname variable. The next property is caller reference. This is a unique value that differentiates calls to create hosted zones. It's required, must be a string, and the easiest thing to do is to just set it as a timestamp. For the value here, create a string template with backticks, then evaluate a call to date.now by surrounding it in the $curly brace syntax. That's just a quick way to get a timestamp as a string. And again, this is to avoid duplicate hosted zones being created. And that's all we'll need for properties. In the next line, create a new const called command. Assign to it a new constructor call of create hosted zone command, passing in the params variable. Then after that, add the return keyword and call send command, passing in command. Now save the file and switch over to your command line and navigate to the scripts 07 directory. Execute the command node create route53 hosted zone.js. Once it's complete, you should see the JSON output for the requests. We need to copy the ID field under hosted zone because we'll need it for our next clip where we'll create a record set for this hosted zone. So go ahead and select that and copy it. Now that we have a hosted zone created, we can add a record set. In your code editor, open the file create route53 record set.js. This is another fairly simple file with only one command to send, but the properties for the record set itself will be quite numerous. So let's start by replacing the string contents of the HZID variable with the hosted zone ID that you copied from the command line output in the previous video. It's important that this value is correct since the route set has to be applied to the right hosted zone for it to work. Now we can implement the create record set function. Create a new const named params and assign to it an object. Make sure not to delete this comment because we're going to need that later to look up a region code. The first property for the params object will be hosted zone ID, which you can give the value of the HZID argument. The next property is change batch. The command we'll be using is actually a change command, which can be used to create, modify, or delete record sets for a hosted zone. It's a different pattern than we've used before, and Route53 is pretty unique in this way. Give the property the value of an object. The object will have one property called changes, which you can give the value of an array. With a single request, you could create or modify multiple record sets by adding different objects to this array. For our case, we're only going to need a single object, so add that here. The first property for this change object is action, which we will assign the value of a string with create in all caps. The next property is resource record set, which has the value of an object. Now, finally, this is the object where we will get to the nitty-gritty details of this change. The first property is name, and this is the DNS name for the record. You could enter a subdomain here, something like demo.hbfl.online or www.hbfl.online, but I'm just going to enter the string hbfl.online so I can create this record for the root domain. The next property is type, and this is the type of DNS record to configure. We're going to do an A record, so you can enter the uppercase letter A here in quotes. Route53 allows you to do basic DNS routing to IPs or more advanced alias routing, which is what we want. Alias routing lets you just point to an AWS resource and Route53 will figure out all the IP and routing stuff. Add the property alias target and give it the value of an object. The first property is DNS name, and this is the internal AWS DNS name. In our case, we're going to send it to the load balancer that we've created. So let's go to the EC2 dashboard. Select the load balancer's menu option and then the load balancer that you created. Copy the DNS name from the details panel. Now paste that DNS name as a string as a value to the DNS name property. The next property is evaluate target health, which Route53 can do to determine whether to route requests or not. We don't really need that, so we can just set that property to false. The last property is the hosted zone ID. Although they are called the same thing, don't get this confused with the hosted zone ID at the root of our params object. This is actually the hosted zone ID of the Elastic Load Balancer, and we can use the link that I put in the comments to find that. Copy the URL I put in the comments and go to it in your browser. This page has all the hosted zones for any region in AWS for load balancers. Look for the region that you're deploying to, and then look in the column that has application load balancers in it. They have created multiple hosted zones for different types of load balancers now, so just make sure you're picking the one with application load balancers. Then copy the ID that's in that cell. Back in your code editor, paste that value as a string as the value for hosted zone ID. And that is going to be it for the params object. In the next line, you can create a new const called command and assign to it a new constructor call of change resource record set command, passing in the params object. I think that might be the longest command name we've used so far. Then on the line after that, you can just return a call to send command, passing in command. Now switch over to your command line and we'll send this record set creation request by executing node create route53 record set.js. Once it's complete, you should get some JSON output like this, showing the status as pending. A quick note here, because these are actual DNS changes, they can take some time to propagate. It's not instant like some of the other changes we've done. If we switch over to the AWS Management Console and go to the Route53 dashboard, you'll see that we have our hosted zone here, and clicking into it, the record set we just created is also here. Even though it shows here, it doesn't mean that the change has propagated live. So even if you're using a real domain name, this A record may have not propagated out into the public internet yet. And that's all for Route53. In the rest of this module, we're going to look at a different way of routing users to your application with API Gateway. API Gateway is one of the newer AWS services, and it reflects an evolution of routing with cloud resources. While there is API directly in the name, it is by no means only for use with APIs. It actually really works well for all types of routing. So what exactly is API Gateway? It's essentially a routing layer that allows you to configure many rules on the same domain and connect it to many different resources. The language of API Gateway is couched in classical REST terms. Each part of a URI path is called a resource, and on those resources you configure methods. Each method can be configured to have a certain behavior and send the request to some AWS service. You can transform the request before sending it on and also transform the response as well. Each method on a resource is configured separately, so you could have different operations on a path going to different AWS resources. It's really flexible and powerful. In this module, we're going to set our demo project up to respond from an API Gateway resource. I'm using this example because you could then see how you could route other paths on that same domain name to other applications. Now let's get started with creating our API in the next clip. There are quite a few parts to actually creating and configuring an API and API Gateway. Each part serves its purpose, but it can be a little complicated when you're just getting started. So I'm going to walk you through it in our script files. Let's get started by opening the createAPIGateway.js file. You may notice right off the bat that the execute function in the script is really large. This is where the API is created and configured. I'll explain each step in just a second. An API in API Gateway is structured like this. You have your API. The API has different resources, which are organized sort of in a tree structure with parents and children. Then each resource can have one or many methods. A method has two main parts to it, the integration request and integration response, where you can manipulate the data going either way. Keep all these pieces in mind because those are what we'll be configuring with this file. So let's look back at our code. Here we're creating the root REST API. We save the response of that creation to a variable so we can use the data from the root API later in the code. Anytime you want to create a resource in an API, you have to give it a parent resource to branch from. In this case, we're using the top level resource, the root API, to branch from. Then we create a resource called HBFL. This will be what our demo app responds on. We have to then create the method and integration for that resource. Then we create one more resource, which is actually a proxy resource. It's basically a catch-all for any request beyond HBFL. It'll be used for things like API calls to our demo project. Once that proxy resource is created, we configure a method and integration for it as well. We're going to need to implement all the functions called in this execute function, so we'll be working in this file over the course of the next few videos. Let's start by implementing the create REST API function. First, declare a params const object. There's only one property needed here, with the key of name. One thing to note with all of these API gateway commands is that the property keys are in camel case, not Pascal case, like every other AWS service. I'm not sure why they made an exception for this service, but in a different version 2 of the API gateway client, they've reverted to Pascal case. So it seems like this might have just been a whoopsie. Give that property the value of the API name argument. Then after the params object, create a new const called command. Assign to it a new constructor call of create REST API command, passing in params. Then on the next line, return a call to send command, passing in command. And that's it for create REST API. The next function we'll implement is get root resource, which will get the root resource ID from the API we just created. The create REST API command does return the ID of the API, but not the ID of the root resource, which is needed to add other resources to. That's why we need this function. Start by creating a params const object. This is another simple object with only one property, with the key REST API ID. The value will be the API.ID property from the API function argument. In the line after the params object, create a new const called command. Assign to it a new constructor call of get resources command, passing in the params variable. Then after that, we want to manipulate the response before returning from this function. So create another const named response, and then assign to it an awaiting call to send command, passing in the command. In the next line, create a new const called root resource. We will go through the resources returned from our command call to find the resource that only has a slash as the path. This will identify that resource as the root resource. After an equals sign, call the function response.items.find, which will look for an item matching some criteria from response.items. Inside the parentheses, add an arrow function with one argument named r. On the right side of the arrow, enter r.path triple equals single quote slash single quote. This will return the single root resource. Then in the next line, add the return keyword and return root resource.id. Now that we have that root resource ID, we can create a new resource off of it by implementing the create resource function. Start by creating the usual params const object. This one will have a few more properties than the other ones. The first property will be parent ID. Give it the value of the parent resource ID function argument. The next property is path part, and you can give it the value of the resource path function argument. This is the path that the resource will be configured to respond to on the final API URL scheme. The last property will be REST API ID, which you can give the value of API.ID. And that's it for the params object. On the next line, add a new const named command. Assign to it a new constructor call of create resource command, passing in the params object. Here's another response we'll need to manipulate. So on the next line, create a new const named response. After an equal sign, add an awaiting call to send command, passing in command. Then in the next line, add return and then response.id. We just need to return that ID property from the response. And that's everything needed for the create resource function. We've implemented the functions to create an API, retrieve a root resource, and create a resource. But there's still more to do. In the next clip, we're going to create a method and integration for a resource. Methods in API Gateway are where you define how a user will actually interact with your endpoint. Each method corresponds with a single HTTP method like GET or POST, and different integrations are added to transform the request or response. Let's get started by implementing the create resource method function in our create API gateway.js file. Start by declaring a params const object on the first line. The first property is authorization type. With API Gateway methods, you're able to create authorizations by using IAM or even your own function. We won't be securing our endpoint. We want it open to the public. So enter the string none in all caps. The next property is HTTP method, which will give the value of the method function argument. Then add the resource ID property, which you can give the value of the resource ID function argument. This is how to tie this method to a resource. The last property is REST API ID, which you can give the value of API.ID. And that's it for the params object. In the next line, create a new const named command. Assign to it a new constructor call of put method command passing in params. Then we can just return a call to send command, passing in command. We won't actually use the response from the command, but there's no harm in returning it. And that's it for the create resource method function. As you can see, there's not much to creating a method either. The interesting stuff with API Gateway comes into play with the integrations. Let's go ahead and move into implementing the create method integration function. Start by creating a params const object. This one will have the most properties in this file. Add the first property named HTTP method, to which you can give the value of the method function argument. The next property is resource ID, which you can give the value of the resource ID function argument. Both HTTP method and resource ID together tell this function which resource method to attach the integration to. The next property is REST API ID, which you give the value API.ID. Then add the property integration HTTP method, which is the method used to call the backend AWS resource. You can give it the same method function argument. Next is the type property. There are several different types of integrations, like sending it to a Lambda function, or using it as a mock, or sending it to an AWS resource. We will use the HTTP proxy type when sending requests over to our load balancer. So add that as the value in all caps with an underscore between the words. And the final property is URI, which we will give the URL to our load balanced demo application. So switch over to the EC2 dashboard and go to the load balancer's menu option and get the DNS name from our load balancer. In the value for URI, the URL does need to include a protocol. So in a string, add http:// and then you can paste the load balancer DNS name. And those are all the properties needed. In the next line, create a new command const. Assign to it a new constructor call of put integration command, passing in params. Then in the next line, just return a call to send command, passing in command. Now our basic method and integration creation functions are complete, which will let us create a basic resource. We do, however, want to also create a pure proxy resource that will handle any requests coming on the HBFL resource beyond the root. There will be some additional code for this, and that's what we're going to add in the next clip. A normal API gateway integration to an HTTP endpoint strips away all of the original headers and only sends special ones from the integration. Sometimes this might be what you want, but other times you want to preserve the initial request to API gateway and just pass it completely over to your HTTP resource on the other side. This operation is called a proxy. In our case, we have several endpoints on our app that serve as API type endpoints, like getting the leaderboards or posting a change in user favorites. We don't want to have to configure a new API gateway endpoint for every single one of these, so we'll create a catch-all proxy resource with the parent being the HBFL resource. So if we call something like HBFL/leaderboards, it will be handled by this proxy method in API gateway and sent on to the load balancer. If we look at our code in createAPIGateway.js, where the proxy resource is declared, we first create the proxy resource by using our createResource function, but passing in this very specific path part. This string, which contains proxy plus in curly braces, tells API Gateway to execute the resource with the rest of the path, whether it's nested or not, whatever it is. Then we use the same method and integration functions that we used before, but we add an additional proxy string as the last argument. You'll also notice the HTTP method we're using is any, which isn't actually an HTTP method, but it tells API Gateway to handle all possible HTTP methods. So because we're using the same functions that we've already implemented, we'll just add some functionality to the createResource method and createMethod integration functions. Let's start with createResource method. After the params const object declaration, add an if and check for the existence of the path parameter, and then create a code block after that. If the path argument exists, we want to configure it as a request parameter on our params object. So add params.requestParameters equals and assign an object. The object will have one property, but it's going to be dynamic. So insert square brackets and then backticks to create a string template. Inside, enter method.request.path.$, open curly brace, path, close curly brace. To the value of this property, add true. Now, what this is doing is telling our resource method that we're going to have a parameter on the path of the URI, the value of which is whatever is passed into the function in the path argument. For instance, in our case, it's going to be proxy. This is basically how you define parameters on your path for a resource method. And this is similar to how you would add query parameters if you were going to use them. Now we can add the new behavior to the createMethod integration function. After the params const object declaration, check if path is truthy, and then create a block, just like we did in createResource method. The first thing we'll modify is adding the path parameter to the URI property on params. So enter params.URI. Then plus equals to add and assign to it. Then backticks to create a string template. Inside the backticks, enter slash, open curly brace, $, open curly brace, path, close curly brace, close curly brace. Mind the multiple curly braces there. This will take our path function argument and add it with curly braces around it to the end of our URI. On the next line, enter params.requestParameters, assigning to it an object. This is where we tie our integration request parameter, which will be going to the load balancer endpoint, to the method request parameter. Similar to the resource method change we made, we'll have a dynamic property key here. Add square brackets and then a string template. Enter integration.request.path.$, open curly brace, path, close curly brace. Then give that property the value of a string template, and inside it add method.request dot path dot $, open curly brace, path, close curly brace. And that will configure the path parameters for proxying. And I'm sure you're done listening to me read out code like that. Now we've got this entire file complete, and boy, does it do a lot. Go ahead and save it and switch over to command line. We're going to be able to run it now, which will be awesome. Run the command node create API gateway.js. It won't take very long before it's complete, and it'll output API creation complete if it succeeds with no errors. Now, since everything is created like this, we can deploy the REST API in the next clip, and then we can actually try it out in our browser. Deployment in API Gateway is kind of unique. There are two key concepts: stages and deployments. API Gateway lets you create stages for your APIs. Think of stages like development, integration, staging, and production. You can deploy your API to different stages to have a healthy development lifecycle. Each time you deploy to a stage, a deployment is created. These are saved in the history of each stage, so you can move between them easily, especially in cases where you might need to roll back. To make our REST API accessible, we need to deploy it, so open up your code editor and open the file deploy API gateway.js. First, we need to paste the ID for your API in this API ID variable. To get this, go to the AWS Management Console and then the API Gateway dashboard. You should see your API titled Hamster API. In this table, there's an ID column with the API ID, so just copy that. And then back in your code, paste it inside the string for the value of API ID. Deploying our API is as easy as just creating a deployment. So let's implement the create deployment function. Create a new params const object. We'll add the first property, which is REST API ID, which you can give the value of the API ID function argument. Next is the stage name property, which you can give the value of the stage name function argument. This is where you could differentiate between stages like prod, staging, or dev, or however you like to differentiate your environments. In the next line after the params object, create a new const called command, assign to it a new constructor call of create deployment command, passing in params. Then in the line after that, return a call to send command, passing in the command. Now, even though this is a create function, you can actually call it every time you make a change to your API, every time you need to deploy it. Each time the function is called, API Gateway will take the current state of your API resource and deploy it to that stage. Simple as that. Now let's move over to our command line and deploy our API by running the command node deploy API gateway.js. After it finishes, it'll output some response data. To get the URL for the deployment, let's go back to our web browser and select that Hamster API option in the API Gateway table. Under Hamster API on the left-hand side menu now, click on Stages and you should see a prod stage. Expand that and you'll see the resources and methods that are deployed. You can see the any method for our proxy was actually turned into all the different HTTP methods. If you click on the get under the HBFL resource, you'll see a prominently displayed link here, which is where the API Gateway was deployed. We need to manually modify this link just a bit, so copy the link and then paste it in a new browser window. Our demo app needs to be accessed with a trailing slash, so add that on the end of the URL and then you can hit enter. Now we're seeing the demo project routing from API Gateway to the load balancer to an EC2 instance. In the next clip, we'll look at limits and restrictions you might find when working with Route53 and API Gateway. Route53 and API Gateway are both constrained by restrictions and limits, but they come from different concerns. Route53 has many restrictions due to the nature of DNS changes, whereas API Gateway has many restrictions due to it being a new service in AWS. Let's look at a few of both. In Route 53, you'll notice quickly that there is a restriction on how fast record set changes are propagated to the internet, and this is based on DNS rules. Usually I found that if you change a record set, the change can be observed almost instantly. If you make an error for some reason though, and need to change that same record set again, the change will be delayed by around 5 minutes. I've encountered this several times, so make sure to be careful when changing record sets. Aside from that, there are the normal resource limits, but they can all be raised by AWS. API Gateway has limits around the number of requests you can make to create, modify, or delete something in your account. These are hard limits and say, for instance, that you can only send 2 create API requests per minute. All the rest are blocked, and then you just have to wait. It's kind of inconvenient. There are also many known issues with API Gateway that restrict certain types of operations. AWS maintains a page with these, found here, and it's a good idea to be aware of some of the issues it currently faces. I ran into some in the past around the way that API Gateway resolves requests and spent a few months figuring it out. Beyond that, there are the resource limits as usual, and those can be raised. In this module, we looked at 2 different ways that you can get your web application to your users. Route 53 follows the classic DNS model but has some tricks up its sleeves. And API Gateway represents a new way of abstracting routing behind a URI and lets you get creative with how a domain routes requests. Let's recap what we covered in this module. We started by discussing the different types of Route 53 routing policies that lets you control where requests route to based on waiting, lowest latency, geolocation of requests, and more. Then we created a Route 53 hosting zone and record set to route to our load balancer. Then I introduced API Gateway and explained how it was structured. After that, we created all the pieces to make a REST API in API Gateway, and then we deployed it. Finally, we looked at limits and restrictions with Route 53 and API Gateway. In the next module, we're going to take a look at other ways to get content to our users by looking at caching static assets in CloudFormation and serving up static sites with S3. Hello, and welcome back to AWS Developer Designing and Developing. In this module, we're going to look at 2 different ways that AWS empowers you to deliver your content to users. The first is CloudFront, a global content delivery network that is essential for providing fast delivery of static files. The second is a feature in S3, and that's S3 static websites. Let's take a look at what we'll be covering in this module. We'll start by discussing the specifics of invalidations with CloudFront. Then we'll create a CloudFront distribution using our existing S3 content. Next, I'll explain how static sites work in S3, and then we'll configure one based on our existing S3 bucket. And finally, we'll look at the limits and restrictions with CloudFront and S3 static websites. Content coming from CloudFront is typically best when being served from the CloudFront cache and not from your origin. Getting this right will dramatically reduce latency to your user. But when configuring cache, you'll set a max time to live before the cache retrieves a new version of the content from the origin. Set the value too high, and when you release new code, then users are still getting the cached version. Set it too low, and you're not taking advantage of what CloudFront can offer. There are 2 real solutions to make the most out of a high time to live value. The first is to invalidate content when you've got a new version available. This can be done by sending an invalidation to CloudFront, defining which files to replace with new versions. A single invalidation can have multiple files to invalidate, even referencing entire directories. But there are a couple of downsides to using invalidations exclusively for handling new content. The first is that there's a hard limit on the number of simultaneous invalidations you can process. While the number is high at 3,000 objects, this essentially places an upper bound on the growth of your application. In addition, you're only allowed 1,000 free invalidations per month. Anything above that has a price associated with it. And to top all this off, invalidations can take some time. They aren't instant. While I've often experienced it takes only a few minutes to process an invalidation, That was with only a few files. I can imagine it would take longer with more files. The second solution, which would work better for many applications using CloudFront, is to treat your assets as immutable and never change them. This way they can be cached the maximum time and never need a manual invalidation. The easiest way to achieve this is to generate a unique name for the object anytime it changes. This might be something as simple as adding a hash to the file name or a date timestamp. Then, when you push a new version of the application, it only references the new files. The first time they're requested, CloudFront retrieves them from the origin and then caches them for the maximum time to live. This has been my chosen solution when working with CloudFront, since it has the side benefit of solving client caching issues as well. In the next clip, we're going to actually create a CloudFront distribution for our static assets.
We've already changed our code to directly access assets in S3, so let's create a CloudFront distribution based off that bucket so that we can get even better performance from it. CloudFront SDK commands might hold the award for most properties in a params object. I seriously made us a completely separate file just because there were so many. Navigate to the scripts 08 folder and open the CloudFront parameters.js file. I moved the two biggest sections of params into this file so that the actual create file will be much easier to read. We've got two sections here, the origin and default cache behavior properties.
Let's get started with adding the origin properties. This origins object can hold one or many origins, so there is a quantity property we'll add first. This tells AWS how many origins will be in the items array. We're only creating one here, so enter the number 1. The next property is items, and it has the value of an array. This is where the origin details will go. Create one object here. The first property for the object is domain name. This will be the domain for your S3 bucket. We'll build it dynamically, so create a string template, then create a variable, and add the bucket name function argument. After that, continue with .s3.amazonaws.com. And with that, we'll build the domain name dynamically based on whatever your bucket name is. The next property is ID. This is going to be a unique value that will be referenced in the other params chunk, default cache behavior. For this value, create another string template, and again, reference a variable with the bucket name function argument. After, add an underscore and the word origin. This will make an ID based on your bucket name, so it should be unique enough for our purposes. The next property is S3 origin config, which has the value of an object. This property is unused by us, but it's required by CloudFront for an S3 origin to work. Give it one property, origin access identity, with the value of an empty string. Like I said, it's unused. Now, that's everything we need to configure for our origin. Let's configure the default cache behavior below to use that origin. These default cache behavior properties do exactly as they say. They configure the default behavior that our created distribution will follow. The first property is forwarded values, which has the value of an object. This will tell our distribution to forward on cookies or query parameters to the origin. In our case, we don't want any of this behavior. Add the property cookies with the value of an object. Inside, give it one property called forward and the value of none as a string. After the cookies property, add a property named queryString and give it the value of false. Now, after the forwarded values object, add a new property called minTTL and set it to 0. This is the minimum time to keep an object in cache before forwarding the request back to the origin. The next property is target origin ID, which needs to match the origin ID we defined above. The easiest thing is to just copy the value from above and paste it here. That way you won't get any typos. Next, add the property trusted signers, which has the value of an object. This will let you create signed URLs for CloudFront content and only allow users to access content that way. We won't be doing that, but this is another required field. Add the property quantity with the number 0. Then the property enabled with the value false. After trusted signers, add a property named Viewer Protocol Policy. This is where you can define HTTPS only, redirect HTTP to HTTPS, or both. I like to redirect HTTP calls to HTTPS, so add the string redirect-to-HTTPS. Next, add the property allowed methods with the value of an object. Here we'll define what HTTP methods can be used with this distribution. We'll have 2, so add a property named quantity with the value 2. Then add a property called items with an array as the value. We'll add 2 methods here, get in all caps and head in all caps. After the items property, add another property called cached methods with the value as an object. This defines the HTTP methods that CloudFront will cache. Add the property quantity with the value 2. Then add the property items with the value of an array. The items here will copy what's above with get and head entered here. And with that, our long properties are complete.
Now we can open create CloudFront distribution.js. Because we're setting up the CloudFront distribution in front of our S3 bucket, you need to populate the value of bucket name with the unique S3 bucket name that you created previously in this course. Now let's implement the create distribution function. Start by creating our params const object. Even though I've offloaded many properties to that other file, we've still got quite a few to add here. So start by adding a distribution config property and giving it the value of an object. The first property inside this will be caller reference, which you may remember from the Route53 hosted zone. This is a unique identifier for the SDK command that we're making. Add a string template with a variable and the expression date.now to get a timestamp for this value. The next property is comment, which is sort of like a description or name for your distribution. It'll be visible on the CloudFront dashboard to help you differentiate it from other distributions. So name it something that will help you distinguish the distribution here. I'm going to put HBFL distribution. The next property is default cache behavior. This is what we set up in the other file. So for the value, call default cache behavior and pass in the bucket name function argument. The next property is origins, which is the other set of properties that we worked on. So set the value to a call to origins and pass in the bucket name as well. The next property is HTTP version, which I like to set to the string HTTP2 to make sure that it's future facing. The next property is price class. Basically, the pricing is set according to how many edge locations that you choose. Add the value price class _100, which is the cheapest, and it only uses edge locations in the US, Canada, and Europe. The next property is IPv6 enabled, which I also set to true to be future facing. We don't really need it right now, but it's good to have. And finally, the last property is the most important. It's enabled, and you want it to be set to true if you want to be able to use this distribution at all. If it's set to disabled, it just won't work. And that's it for the params object. On the next line, create a new const called command and assign to it a new constructor call of create distribution command, passing in the params. On the line after that, return a call to send command, passing in command. And that's it for this function and file. Now we can create this script to create our distribution. So switch over to your command line and navigate to the scripts 08 folder. Execute the command node create CloudFront distribution.js and then wait for it to finish. CloudFront distributions can take some time to set up after we get this response back from the command line. So in the meantime, we can go and we can modify our demo project. First, we need to get the new domain name for our CloudFront distribution. which is available even though the distribution is still deploying. So go ahead and open the AWS Management Console and go to the CloudFront dashboard. Find the distribution by either the comment or the origin, and then copy the domain name from the table. Now, just like with S3, there are only a few places we need to update static references in our code. The first is in util/assets.js. So go to that file in your code editor. Copy the value into the base const on line 1. You will need to add the HTTPS protocol to the domain also. So make sure it looks like this. Now, one more place. Go to handlers/template/index.html. And then on line 5, update the URL and take out any bucket that's on the path. Just leave the file name at the end. Do the same on line 7 with the favicon, and then also on line 12 with the JavaScript import. Now, to fully test this out, you need to follow all of these steps. Because this video is already long enough, I'm not going to be walking you through them. You'll just need to follow them on your own. So you'll need to rebuild the project locally, deploy the code out to your EC2 instance, upload the files to S3 again, repopulate the Dynamo table, and finally wait for the CloudFront distribution to finish getting set up. You can then test out the changes with the load balancer URL, or you could use the fancy API gateway URL we did in the last module. A lot of steps, but our application is becoming really robust. It's using a ton of AWS services, and the speed of the application is getting really fast. So for the rest of the module, we're going to take a look at how static websites work with S3.
Static website hosting with S3 is one of AWS's oldest solutions, launching shortly after S3 itself. And while AWS has since released other services that provide similar functionality, S3 static hosting still continues to be one of the easiest to configure and work with. Let's take a look at how it works. First, let's look at the difference between a website and an S3 bucket. With an S3 bucket, you use keys to get back objects. Every object must be referenced directly, and only that object is returned. It's just like getting static assets. A website is different because you can reference a path and some HTML will be returned to you. You don't have to reference the file where the HTML is explicitly. In many ways, that's what S3 static hosting is really providing. It's letting you configure some static behavior to occur when a directory is referenced in the URL. With S3 static hosting, you configure what the name of your index file will be and what the name of your error file will be. The defaults are index.html and error.html. Then you can place these files in any directory in your S3 bucket, and they will be returned when that path is navigated to. In addition, S3 static website hosting gives you a unique URL to use to get to the site root. There isn't too much complexity involved, but it provides a simple solution when you need a simple site. In the next clip, we're going to get a static site set up using our existing S3 bucket.
In order for us to get to try out a static S3 site, I've made a simple splash page for Hamster Ball Fantasy League. The files are already in your S3 bucket with the index.html file and a style sheet in the static folder. We'll configure our existing S3 bucket to serve a static website, and then that content will get served. In your code editor, open the file configure s3website.js. The first change is to update the name of your S3 bucket for the value of the bucket name variable. Now we can implement the configure S3 site function by first creating a params const object. The first property is bucket, which will give the value of our bucket name function argument. And then the next property is website configuration, which will need the value of an object. This is where we're going to tell S3 how we want the site to operate. There are really only two options for properties that you could use here: index document or error document. We could add error document and provide an error.html file, but I didn't bother making one, so we'll just leave that out for now. Go ahead and add the property index document and give it an object as the value. This tells the site what file to use as the index. In the object, add the property suffix and give it the value of index.html as a string. You could put something else here if you wanted, say a file like static.html to load as the index of the site. We just already have index.html in there. Now, index.html is actually the default for this property, so we didn't necessarily have to add the property. I just wanted to make it explicit how this was working, kind of a learning experience for you. So that's it for the params object. In the next line, create a new const called command and assign to it a new constructor call of put bucket website command, passing in the params variable. Then on the line after that, just return a call to send command, passing in command. And that's it. It's pretty simple to configure an S3 site. Now switch over to your command line and execute node configure s3 website.js. Once it finishes loading, unfortunately, it doesn't actually give us any useful output, such as the domain name that we would want to use to see the site. So switch over to the AWS Management Console and go to the S3 dashboard. Click into your hamster bucket and then go to the Properties tab. At the bottom of this page is a section for static website hosting. This hyperlink at the bottom is clickable, and if you visit it, you'll be taken to our static site being hosted with S3 static website hosting. Again, this isn't the full HBFL site, it's just a static file to demonstrate these S3 static sites. In the next clip, we're going to look at some limits and restrictions with CloudFront and S3 static website hosting.
While most AWS services have limits to be concerned with, S3 static websites have none. The only limits they have is in relation to normal S3 limits. CloudFront, however, does have a few limits to be aware of. Most of them are just soft limits on the number of resources, but there are some limits on how you configure your distributions. You can only have a single SSL certificate on a distribution, so you'll have to expect multiple distributions in your design if you require multiple certs. There is no limit on the number of objects that CloudFront can serve, and only a soft limit on the number of distributions. There are limits with invalidations that I mentioned earlier, and those are not soft limits, so do be very cautious with that. But other than those few caveats, CloudFront can likely handle whatever you throw at it. In this module, we looked at a few different ways to deliver content to your users. CloudFront finds its way into most web projects, but S3 static hosting is a little more of a special use tool these days. Let's recap what we covered in this module. We started by discussing CloudFront invalidations and why you might not want to use them. Then we created a CloudFront distribution with all of those parameters. Next, we moved on to S3 static websites and set one up based on our existing S3 bucket. And finally, we looked at the few limits concerning CloudFront. In the next module, we're going to look at inter-service communication inside AWS. Both Simple Queue Service and Kinesis streams provide ways for services to decouple and communicate in an asynchronous manner. Hello there, and welcome back to AWS Developer Designing and Developing. In this module, we're going to look at two different ways to communicate between services or applications. Simple Queue Service, or SQS, is a way to send messages via a queue system. Individual messages can be taken off the queue and processed by consumers. Kinesis streams are a real-time stream-based messaging service that works similar to SQS, but with subtle differences that change the ideal use case. We'll be looking at both in this module and configuring them to work with our application. Let's go over what we'll be covering in this module. We'll start by looking at some of the specifics of polling in SQS and how messages work. Then we'll create an SQS queue to send race results, and look at how to consume and process those messages. Next, I'll introduce you to Kinesis streams, and we'll set one up for our application to send race results to the races table. And finally, we'll cap it off by looking at some of the restrictions and limits with both services. SQS works on a process of clients sending messages to the queue, and then consumers polling for messages on the queue. This is sort of like the life cycle of a message in SQS. With sending messages, the process is simple enough. The messages are just sent and the client continues on. But polling is a different story. What happens when there are multiple consumers polling a single queue? What happens if a consumer polls for messages but then can't process them? SQS has solutions for these scenarios, which is what we're going to talk about here. When a message comes into the queue, it may or may not be visible to consumers immediately, depending on the delay seconds attribute. This delay seconds attribute will delay the visibility of a message in the queue for a given number of seconds when the message initially arrives in the queue. Once the message is visible and a consumer reads it, another attribute comes into play, the visibility timeout. Once a message is read, it is considered in flight. This means the message is still in the queue, but it's not visible to consumers. Until the visibility timeout runs its course, the message will stay in the queue and be invisible. If the visibility timeout runs out, then the message becomes visible to consumers again, and they can then read it, which starts the visibility timer all over again for that message. Because of this, a consumer should delete a message once they finish processing the message. The visibility timeout gives consumers time to process messages and then delete them. Here's a diagram showing the life of a message with both delay seconds and visibility timeout. In this case, the message isn't deleted, and so it becomes visible again for consumers. But in this next diagram, the message is deleted in time by its consumer. This is the ideal life cycle for a message in SQS. Both the visibility timeout and delay seconds can have default values set on the queue, but each message added to the queue can override those values and provide specific delay seconds when sending a message or specific visibility timeout seconds when consuming messages. Another default value you can set on your queue is how long consumers should wait when they're polling for messages. This can be set up to 20 seconds. If any messages are available or come available while the consumer is waiting, the consumer will immediately return with the new messages. This is called long polling, and it can be useful because you are charged for SQS by each request made. Requests are either a request to read a message or to write a message. So by using a balance of long polling and how frequently you read messages, you should try to strike a good balance that makes it economically feasible to use SQS for messaging and also highly performant. In the next clip, we're going to create our SQS queue for sending race results.
The first step in using a queue in SQS for communication between services in AWS is to actually create the queue. Let's start by opening the file in the scripts 09 directory named createsqsqueue.js. Since there's quite a bit of code required to work with queues, I've actually done most of the work and will just be filling in certain parts of the code, mostly properties. In this file, you'll only need to create the params object for the create queue function. So go ahead and start by creating the params const object. The first property is queueName, which we can give the value of the queueName function argument. The next property is attributes, which has the value of an object. Most of the properties we'll add here are ones that I actually mentioned in the last clip. The first property here is going to be delay seconds, which is the default delay seconds for each message. We can just set it to the value 0. Remember, an incoming message can override this if they want to. The next property is message retention period, which is how long the messages will stay in the queue if they're not read and deleted. We'll set this to the number 345,600, which is the seconds equivalent to 4 days, if you ever need that number. Next, add the property visibility timeout, which is how long messages will be invisible after being read. We can set it to the value 30 for 30 seconds. Then the last property is receive message wait time seconds, which will set the long polling time of a consumer. We can set this to the value 0 and let consumers decide whether they want to long poll or not. Now the create script is ready, so we can save that file and switch over to your command line and then navigate to the scripts09 folder. Then you can execute node create sqs_queue.js. Once it's complete, it'll output the URL of the queue, which is very nice, but we don't actually need to keep it for now. Now in the next clip, we're going to configure our demo project to send messages to this queue. Our demo project has the ability to run a sort of simulation for the hamsters and their races, a fantasy simulation. Since this is sort of a real-time operation, I thought it was a good use of SQS. Normally, you'd want to have another service on the other end consuming messages, one to send, one to consume. But for our demo, we'll have the same application send and receive messages. Let's start with the sending. In the lib data lib folder, there is an sqs.js file. This is a file that will send the results of each race simulation. Pushing a message to a queue requires you to have the full queue URL. And I've abstracted this push function so that it only requires a queue name, and then it will go and retrieve the queue URL before it starts pushing to it. So the first step in this function is to get the queue URL. So inside the push function, create a new const and we'll name it queue params, not regular params. You can assign an object to that. It'll only need one property, queue name, which you can give the value of the queue name function argument. Then after that, create a new const named queue command. Assign to it a new constructor call of getQueueURL command, passing in the queue params object. Then in the next line, create a new const called queueResponse and assign to it an awaiting call of client.send, passing in the queue command. This is going to retrieve the URL for our queue based on the name. Next, we will create a new const named sendParams and assign to it an object. This is going to store the properties for our send message command. The first property is going to be message body, which is the message that we want to actually send and put on the queue. We will need to turn the message function argument into a string. So call json.stringify and then pass in msg, message. The next property is queueURL, and you can give it the value of queueResponse.queueURL. Then after the send params, create a new const named sendCommand and assign to it a new constructor call of sendMessage command, passing in the sendParams variable. Then on the line after that, return a call to client.send, passing in sendCommand. And that's all we need to do to send a message. In the params for our sendMessage command, you can optionally include things like delay seconds and visibility timeout if you want it to be different than the defaults that are on the queue. And with that, we're done making our changes for sending messages. In the next clip, we'll implement queue polling for the demo project. Now that we're pushing race results messages up to SQS, we need to poll for those messages and then update the data sources with those records. We'll make our first changes in the lib data lib folder with the sqs.listener.js file. This file will poll for SQS messages every 5 seconds. If messages are received, if there's something there, then it will modify the master records in DynamoDB. If you remember the explanation of long polling, this interval of 5 seconds when polling is likely too short for production applications, since it will incur a fairly high cost. With one instance, it'll make around 500,000 requests a month. So definitely do use a better value if working with real-world applications. This init function is what starts the interval timer for polling, and it calls the poll function to actually poll the queue. Let's add the properties necessary by completing all the to-dos in this file. The first step is to get the queue URL. So let's add the single property for queue params. The key will be queue name, and you can give it the value of the global variable race_queue, all in caps. That's done. So look further down for the receive params object, and this is used to poll and receive messages from the queue. The first argument is queue URL, which you can set to the queuedata.queueURL value. The next argument is max number of messages. This is a value between 1 and 10 and is basically the maximum number of messages that will be retrieved. The default is 1, but I like to set it to 10 to get as many as possible in one request. The last property is visibility timeout, which I'm going to set to 15. This is just an example of overriding the queue default. There's not any reason to do it here. I just wanted to give you an example of that. Now that's all the changes necessary for the poll function. Once we receive and process a message, then we need to delete it. So scroll down to the delete messages function. We need to add properties to send to the delete message command. The first property is queue URL, which you can give the value of the queue URL function argument. The next property is receipt handle. This is basically a unique value provided each time a message is retrieved. This is how the queue knows which actual message to delete. We can give it the value of result.receiptHandle to reference the message that was received. You may notice this function is called in a for loop, so each retrieved message will have this delete message command called on it. There's also a delete message batch command in the SDK that could also have worked well here since it deletes many messages. So you can take your pick. With that change, our listener is ready, and we just need to enable all the functionality in the index.js file at our project root. At the bottom of the file on line 87, there is a commented line that calls the queueInit function. This is going to turn the listener on and have it start polling the queue. So go ahead and just uncomment this line and save the file. Now our changes are done, and you could try running them now, deploying them up to EC2, but it'll probably be easier to wait until we finish the rest of the work on our Kinesis streams, which we're going to do with the rest of this module.
Sometimes SQS isn't good enough for your application use case. You could want to avoid the polling process, or you find that you want a more real-time solution. There might be many reasons why SQS won't work, but Kinesis Streams might be perfect for you. Kinesis Streams is a service for real-time data transfer. It scales easily and can have multiple producers and consumers. It doesn't have fine-grained control over how messages are handled like with SQS, but that simplicity might make it better in some situations. Let's talk about one of the key concepts in Kinesis Streams, and that is sharding. Sharding is the capacity unit used with Kinesis Streams. One shard is equivalent to your Kinesis stream having 1 megabyte per second of input and 2 megabytes per second of output. If you need more input or output, you would add shards to your stream. We're going to use a Kinesis stream to push our hamster race results, similar to the queue, but the consumer of the Kinesis stream will update the races instead of the hamsters. In our case, we're going to use a Lambda as the consumer. One of the main reasons is that because a stream is real-time, it requires a dedicated consumer, and our web application is not really the right fit. Lambdas are actually a great fit as Kinesis consumers, so this will give you a taste of how that can work. Now in the next clip, we're going to create our first Kinesis stream.
Now that we understand what a Kinesis stream is and how it works, let's go ahead and create our first stream. open the create kinesis stream.js file in the scripts 09 folder. This is going to be another one of those very, very simple files. We just need to implement one function, so let's implement create kinesis stream. You can start by declaring a params const object, and then the first property will be shard count, which is the number of shards that will be created in the stream. You can modify this value later on if the stream needs to increase its capacity, but for now we'll just enter the value 1 here. The next property is stream name, and we can give that the value of the stream name function argument. And that's it for the params object. On the next line, you can declare a new const called command and assign to it a new constructor call of create stream command and pass in the params variable. Then after that, just return a call to send command and pass in that command variable. And that's it for this script. You're definitely getting the hang of this now. Let's create the stream now by switching over to your command line. Execute the command node create kinesis stream.js. When it's complete, the process will finish and it has no useful output for whatever reason. In the next clip, we're going to start sending race results to this kinesis stream. Now that we've created a kinesis stream, we need to start sending records to it. Let's start by just taking a look at a file. Go to the lib simulation folder, haven't been here before, and open the resolution.js file. This file is used once the simulation is complete and the records need to be sent to SQS and Kinesis. On lines 8 and 9, we define variables for the stream name and partition key. The partition key is a value that Kinesis hashes and uses to segment the data record to a specific shard. Even with a single shard, which is what we have, this is still a required field when pushing data to Kinesis. These values will be used when we call the send function. So let's implement that function by opening the kinesis.js file in the lib data lib folder. This is another very simple file that only performs one operation. The only thing we need to do is to add properties to the params object in the send function. As you can tell, as time goes on, I'm doing more and more code for you. I'm sure you're getting tired of me repeating the same things over and over. So the first property we're going to put here will be data, which is what we'll actually be sending to the Kinesis stream. This needs to be a buffer object. So first call buffer.from. Then inside the parentheses for that, we need to stringify the message. So call json.stringify, passing in the message function argument. That will provide the Kinesis stream with the message in the format that it wants. The next property is partition key, which we can give the value of our partition function argument. And then the final property is stream name, which will have the value stream name. It's pretty simple, just point the data at a stream and put it up there. We use the put record command to actually send that message. And that's all there is to it. Now in the next clip, we are going to set up our stream consumer. For this course, we're going to use a Lambda function as a convenient Kinesis stream consumer. What's easy about this is that you can configure a Lambda function to be triggered directly from a stream, meaning that you don't have to create some long-running application to consume all of this Kinesis stream data. Lambda functions are event-driven, so the function will be invoked anytime data comes into the stream. So we'll start by creating our Lambda function. In the scripts 09 folder, open up the create kinesis consumer.js file. Now to configure a Lambda function to connect to a Kinesis stream, you will need the ARN for the stream. So to get this, we're going to move over to the AWS Management Console and go to the Kinesis dashboard. Click on the number in the data streams section, and then click on the hamster race results option. And then you can copy the ARN, which is found here. Now switch back to your code editor and paste the ARN for the value of the Kinesis ARN variable. Now the rest of this file creates a role for your Lambda function with permissions to read from a Kinesis stream. and then it zips up the code that will run on the Lambda function. It creates the Lambda function, and then it creates the trigger that connects the Lambda function and the Kinesis stream. If you scroll to the bottom of the file, you'll see the create trigger function. This is the only other part of this file that you'll need to modify. We just need to add the properties to the params object that will be passed to the create event source mapping command. The first property will be event source ARN, which will give the value of the Kinesis ARN function argument. This is what we needed that ARN from the stream's dashboard for. The next property is function name, which is the name of the Lambda function. Give it the value of the Lambda name function argument. The next property is starting position, which tells the Lambda function at which record it should start processing from the stream. You can just enter latest in all caps as a string, since this connection will be set up before there are even any records in the Kinesis stream. So latest is fine. Finally, add the property batch size and give it the value 100. This defines how many records will be retrieved at one time from the Kinesis stream, and 100 is the max value here. And that's it for code that we need to modify. I do want to show you the code that will be running on the Lambda function, so look in the Lambda Kinesis consumer folder and open the index.js file. This file doesn't actually have any code that's interacting with Kinesis. The Lambda will be invoked whenever the Kinesis stream has records, but that data will come in as an array in the event.records property. On line 12, you can see how to get the actual data from the Kinesis record that's there. You don't have to go to Kinesis in any other way. It will be a base 64 encoded buffer, so it does need to be processed correctly before you can really do anything with it. And then the rest of the Lambda function just puts the Kinesis record data into the DynamoDB races table. Now we can switch over to our command line and run the command node create Kinesis consumer.js. This will take some time to run because the role creation isn't immediate. So I'm speeding up the video here a bit, and then you'll see the output for the trigger creation in the console. Once created, you don't need to do anything else with the Lambda function, since it's live and it's connected as soon as it's created. Here's a good point where you can actually try everything out. To test it, you'll just have to redeploy your app to the EC2 instance. Use the same deployment script that we used earlier, just make sure the IP address is still relevant, still the right instance. Then when the code has been redeployed, to run the simulation, you'll log into Hamster Ball Fantasy League using the username Ryan and the password pass. And then you'll click the gear next to the username and then click the Run Simulation button. If you've already run the simulation, you can also click Reset Results if you want to start fresh. And that's it for SQS and Kinesis streams. In the next video, we're going to look at some of the limits that exist with both of those.
SQS and Kinesis streams are highly performant services targeted at specific use cases. Understanding how the systems work and the restrictions around them are essential for designing a robust web application. In the previous discussions, we've covered most of the limits around SQS and Kinesis streams, and of course they both have the soft resource limits that can be raised. But there are a few Kinesis stream limits I wanted to mention here. The first limit with Kinesis streams is the limit to the size of the data blobs you can send through a Kinesis stream. They are static at 1 megabyte. This is basically constrained by the size of the shards making up your stream. If you have data larger than that, you'd either need to break it into pieces or send records of S3 keys where the data is actually stored. In relation to sharding, there's a limit around the number of put requests operations you can perform each second, and that is 1,000 per shard. If you find yourself hitting that limit, you'll need to scale your stream up by adding shards to it. And those are all the major limits with SQS and Kinesis streams. Between SQS and Kinesis streams, you should be able to find a solution for any messaging need you have. SQS provides a more distributed and decoupled form of sending messages. and Kinesis provides real-time and high-throughput streams. Let's recap what we covered in this module. We started by discussing some of the details of SQS, like delay seconds and visibility timeout on messages. Then we created a queue and changed our app to send race results through a queue to update the hamsters table. Next, I introduced Kinesis streams, and then we again sent race results into the stream, while the Lambda function consumed them on the other end and updated the races table. Finally, we covered the limits regarding SQS and Kinesis streams. In the next module, we're going to look at some communication tools in AWS, like the Simple Notification Service and CloudWatch alarms. Hello, and welcome back to AWS Developer Designing and Developing. This is the last module for this course, and we're going out with a bang by covering two services that will increase the real-time nature of your applications. Simple Notification Service, or SNS, is used to send notifications to users via SMS, email, HTTP, and many other ways. A usual trigger of SNS is CloudWatch alarms, and those can be configured to make sure that your application and services stay up and healthy. Let's take a look at what we'll be covering in this module. We'll start by creating an SNS topic and subscribing to it with your mobile phone or email. Then we'll modify our demo project to publish race results to the topic and give it a whirl. Next, we'll create a CloudWatch alarm to monitor our application health and send notifications if something happens. We'll end out the module discussing some limits around SNS and CloudWatch alarms. And then we'll have a special clip on what resources to delete as you're cleaning up your AWS account after this course.
Topics in SNS are single elements where consumers can subscribe. When any message is published to the topic, all of the subscribers are sent that message over whatever protocol they have configured. This is essentially how SNS, Simple Notification Service, works. In this module, we're going to set up a topic and subscription so that we can send notifications whenever races are complete. We'll start in this clip by creating the topic that will have messages published to it. Open up the file in the scripts 10 folder named create_sns_topic.js. We only need to implement the create topic function in this file. So let's start by creating a const named params and assign to it an object. The first and only property for this object is going to be name, which you can give the value of the topic name function argument. Topics are super simple, as this is actually the only required property for the create topic command. Now in the next line, create a new const called command and assign to it a new constructor call of create topic command, passing in params. Then in the line after that, return a call to send command, passing in command. This file is now complete, pretty easy. So we can switch over to our command line to run it. Navigate to the scripts 10 folder and execute the command node create SNS topic.js. You should get an output with this topic ARN, something that we're going to need later, so don't get rid of this output. This will signify that your topic has been created. And now that we've got a topic, we need someone to subscribe to it, which we'll do in the next clip. One of my favorite things about SNS is the different types of notification options that are available. You're not only able to send emails, but also SMS, hit HTTP endpoints, trigger Lambda functions, or even send the messages to an SQS queue. We'll keep it real low-key for this course and just set up an SMS notification. We do want to know what happens with the hamster races after all, don't we? Open up the create SNS subscription.js file. We'll start by adding a few values. We need a mobile number to send notifications to, so add your mobile number, including the country code and no hyphens, just the numbers, as the value for the endpoint here. If you've got an American phone number, your country code is 1. You're welcome. Then on the next line, we need to enter the ARN of the topic we just created. You can get that from the command line output from when you created the topic. Copy this topic ARN value right here, and then paste it as the value for topic ARN. Now we're ready to implement the create subscription function. Go ahead and start by creating a params const object at the top of the function. The first property is protocol, which we are passing in as the function argument type. The next property is topic ARN, and you can give that the value of the topic ARN function argument. The last property is endpoint, and you can give it the value of the endpoint function argument. These are the only 3 properties you need to subscribe to a topic. On the next line, create a new const called command. Assign to it a new constructor call of subscribe command passing in params. And then after that, you can return a call to send command, passing in command. This will make our file complete. So let's switch over to the command line to run it. In your command line, execute node create SNS subscription.js. It'll output the subscription details, and you should be up and running. In the next clip, we're going to implement a library in our demo application so that it can send notifications to SNS. Now that we have a topic with one subscription, any message published to that topic will be sent to the subscriber. I've prepared some of what you need to do this. We just need to implement a publish function. In your code editor, navigate to the lib data lib folder and open the sns.js file. This file exports a publish function that can be used to send a notification to the SNS topic. Let's get started completing this file by pasting the ARN for your topic to the value of topic ARN. You may still have it in your clipboard, but if not, you can go back to your command line and copy it from the create topic output. Now let's implement this publish function. Create a params const object on the first line here. Just like the topic creation and subscription, there aren't many properties required. The first will be topic ARN, which you can give the value of the topic ARN variable that you configured above. The next property is message, which you can set to be the MSG function argument. Now with our properties set, let's publish out the message. In the next line, create a new const called command. Assign to it a new constructor call of publish command, passing in params. Then after that, return a call to client.send, passing in command. And that's all the changes we need to complete adding SNS functionality to our demo app. Now in the next clip, we're going to configure a CloudWatch alarm to keep our application safe. When you're working with many AWS services, CloudWatch alarms may be created for you. A great example is the auto-scaling group that we configured. With target tracking enabled, AWS created 2 CloudWatch alarms, one to scale up and one to scale down. But sometimes there are specific things that we care about that we want to create custom CloudWatch alarms for. In that case, there are hundreds of different metrics for different services that CloudWatch lets us set alarms on. In this clip, we're going to set an alarm on our load balancer to send a notification to our SNS topic if the healthy hosts fall below 1. This basically means if something happens to our application instance and it stops responding, we should get a text message. All of these details will be wrapped up in a single CloudWatch alarm. We'll create this alarm using the create CloudWatch alarm.js file in the scripts 10 folder. We'll start by filling in these to-dos for variables. First, we need to paste that SNS topic ARN again for the value of topic ARN. I'm kind of thinking that by now you might not have access to it on your command line anymore, so I'll show you where you can find it in the AWS Management Console. Go to the SNS dashboard. Click on the Topics menu option on the left, and then you should see your topic there with the ARN in this right-hand column. If you copy that value, then you can paste it in the string for the value of topic ARN. Next, we need to get parts of the target group ARN and load balancer ARN from the resources that we created towards the beginning of this course. So head back to the AWS Management Console and go to the EC2 dashboard this time. In the left-hand menu at the very bottom, select Target Groups, and then select the target group named Hamster TG. And then we're going to just grab a part of the ARN, not the whole thing. Select from target group / hamster TG all the way to the end of the ARN. This little section is all that CloudWatch needs to set up the alarm. So switch back to your code and paste that as a string for the value of TG. Now we've got one more, and that's for the load balancer. So back in the EC2 dashboard, select the load balancer's menu option on the left. Then select the entry named hamster LB. And in the details for the ARN value, we're going to select everything from app / hamster LB to the very end and copy that little section. Then back in your code, you can paste that value as a string for the value of the LB variable. Now that we have all those values completed, we can get started on implementing the create CloudWatch alarm function. First, create the params const object. We've got quite a few parameters here in no particular order, so hold on to your hat. First, add the property alarm name, which can have the value of the alarm name function argument. This will be the alarm's identifier in CloudWatch. The next property is comparison operator, and the value will be the string less than threshold. This is the check that the alarm will do. We want it to see when the healthy hosts for the load balancer are less than 1. That's why we chose less than threshold here as opposed to greater than threshold. We'll define the threshold below. Next, add the property evaluation periods and give it the value of 1. This lets you define how many periods to evaluate if the value is less than the threshold before going into the alarm state. In our case, we want to know immediately, so we'll set this to 1. The next property is metric name, which will assign to the string healthy host count. There are tons of these metrics, but this one gives us the correct analytics for the load balancer hosts. The next property, namespace, refers to the AWS service that the metric is a part of. The value for this is a string with the value AWS/application ELB. The next property is period, which works with the above evaluation periods property. This says how long a period should be defined as in your alarm. The typical length is 5 minutes, but I actually prefer 1 minute for this. This value should be in seconds, so enter the number 60. Next is the threshold property. In our case, this is the number of healthy hosts that are okay. This threshold is based on the metric that you selected. We'll enter 1 here since we want the alarm to go into alarm state if it's less than 1. This property is directly tied to the comparison operator above. You'll notice it says less than threshold, and this is the threshold property. The next property is alarm actions, and it has the value of an array. This will basically be the actions the alarm takes when it's triggered. Enter the topic ARN function argument here. The fact that this is an SNS topic tells the alarm all it needs to know, and it will publish an alarm to the notification topic. The next property is dimensions with the value of an array. This is where you specify exactly which resources the alarm should gather metrics from. For healthy hosts, we need to enter both the target group and load balancer resources here. Create an object, then add the property name with the value of target group as a string. The other property of this object is value, with the value as the TG function argument. Now we'll make another object in this array. The name property for this one will be load balancer, and the value property will be the LB function argument. Now outside the dimensions array, add the statistic property, and give it the value of average as a string. Other possible options here are minimum, maximum, sum, and sample count. Minimum would probably also work for our purposes. And the final property is treat missing data. This property defines what the alarm should do if it is missing appropriate data. We'll add the string breaching here as the value in all lowercase. This means that if there is missing data, if it can't tell how many healthy hosts there are, it should trigger the alarm. Other possible options for this are ignore, not breaching, or missing. The reason that we're going to be putting breaching here is because if you reach 0 healthy hosts on your load balancer, instead of the metric showing up as 0, it actually comes in as missing data. So for us, a missing value here basically equals 0. Thus, we want the alarm to fire. And that's it for all the properties. In the next line, create a new const called command, and then assign to it a new constructor call of put metric alarm command, passing in the params variable. Then you can just return a call to send command, passing in the command. And that is all we'll need to create our alarm. Let's run the file by switching over to your command line and executing node create CloudWatch alarm.js. And you don't really get any useful output when it finishes completing, but once it does, the CloudWatch alarm is now configured to alert your hamster topic whenever your load balancer goes below 1 healthy host.
There aren't many limits when it comes to SNS or CloudWatch alarms. This is mostly due to their simple operations. CloudWatch does have a few more than SNS, so let's take a look at the limits that do exist. One restriction to be aware of with SNS topics is the allowable characters in a name. Only alphanumeric characters, hyphens, and underscores are allowed. Unfortunately, emojis aren't supported. Amazon really needs to get on it though. CloudWatch has a limit of 5 actions that can take place per alarm. This is a hard limit and can't be changed. If you need more actions, you could create a new CloudWatch alarm with the same metrics, but that might end up being pretty messy. In addition, a CloudWatch alarm period can only be a maximum of a day. Remember, the period is used to decide whether the alarm should fire or not. If you're looking for more lengthier time frames than a day, then CloudWatch is probably not the best solution to make those evaluations. The last restriction is that even though CloudWatch does have a mechanism for creating custom metrics, you are restricted by the metrics that AWS makes available. For instance, if we wanted an alarm created whenever Zepto the hamster came in 6th place 3 times in a row, we'd have to look for another place to figure that out. We all know Zepto is a winner though, and that would never happen, so maybe this is just a moot point. And that's it for limits and restrictions. In the next clip, I want to give you a guide for cleaning up everything we've created in this course. Throughout this course, you've likely created a lot of resources. I thought that making a list of what you need to clean up after might be helpful. So let's look at what you need to clean up and how to do it. We'll start with the EC2 dashboard, where most of our resources are located. You'll first want to delete the load balancer, then the auto-scaling group, then the target group. Once those are gone, you can kill any instances still around. Delete the AMI we created, and then delete both key pairs, since there aren't any more live instances using them.
Delete the launch template used to make our instances.
Delete any EBS snapshots that were created, and any EBS volumes that are still around. Finally, delete any security groups, other than the default one. Next, go to S3 and delete the hamster bucket. Then go into RDS and delete the MySQL instance. Don't bother taking a final snapshot of the database, unless you're really nostalgic about the results of the Petco 2000. Now go to DynamoDB and delete both tables. Then go to Elasticache and delete the Redis cluster we created.
You can go into Route53 and delete the record first, and then the hosted zone. Then go into API Gateway and delete the hamster API that we created. Now go to CloudFront and delete the hamster distribution. You do have to disable it first, and then once it undeploys, then you can actually delete it.
We're almost done. Head into the SQS dashboard and delete the queue we created. Then go to the Kinesis Streams dashboard and delete the stream we made. We also have that Lambda consumer, so go into the AWS Lambda console and delete that function. Finally, go to SNS and delete the hamster topic, and then go to CloudWatch and delete the healthy hosts alarm. There are some resources that are still around in IAM, but they have no cost, so you can delete them at your discretion. And that's it. It's hard to believe we can delete so much work in such a short time. While SNS is powerful and quite useful, when coupled with CloudWatch alarms, the true potential of real-time notification is realized. There are an endless number of uses for both services, so I hope this module has inspired you to try out things with each. Let's take a look at what we covered in this module. We started by creating an SNS topic. Then we made an SNS subscription with that topic and your mobile number. Next, we modified our app to send notifications to the topic and ultimately our mobile phone when race results were finished. Then we created a CloudWatch alarm and hooked it up to notify us through the SNS topic. Finally, we looked at some of the few limits on SNS and CloudWatch alarms. And we've reached the end of this course, AWS Developer Designing and Developing. I sincerely appreciate you taking this journey with me to learn more and more about AWS. At this point, you're in a good place to start doing some damage in AWS. Find a personal project or side project at work that allows you to try out some of the services discussed in this course. And consider finishing the other courses in the AWS Developer Certification path to prepare to master the AWS Developer Associate Certification exam. Again, my name is Ryan Lewis, and thank you for watching this course.